So it's a great pleasure to have Pratik here. He's going to give us a set of 3 lectures on closed universes versus AdS.
Thank you so much. Thank you so much for the invitation. Firstly, I'd like to start by thanking all of you for letting me be back home after so long. It's great to be back here. And so this is going to be a set of lectures that's roughly going to be with the theme of this paper that I wrote a year and a half back with Stefano Antonini. And there's been a lot of recent discussions around this topic. So I'd like to sort of bring out the sort of discussions that have come out and why it's interesting to people and so on.
All these junior people like Witten and
yeah, like people like Witten are following up and stuff. Yeah. I hope he's not giving us. Okay, so but first I'd like to sort of bring up the context in which this came out. So this, I mean, the theme will be to try to talk about this paper, but there's really been a lot of work that's gone into this, and there's a sort of overarching theme relating the information paradox, this sort of idea. So I'd like to first bring that up. So the first lecture will roughly be about, it's going to be a lightning review of the information paradox with focus on certain things that will become relevant to what we're going to discuss later and how it's really part of the same sort of discussion. The second lecture will be more specifically about constructions of closed universes in the context of AdS CFT and how we can think about the closed universe Hilbert space in AdS CFT. And then finally, the third lecture will be more focused on specifically this paper and what the puzzle is and various discussions around how one could try to resolve it. Okay. So at least, yeah, I hope to make this as pedagogical as possible. So especially for students, please ask as many questions as you'd like. In the first...
Does that invitation extend to faculty?
No, at TIFR, it's not like I have to tell you.
What he's really trying to say is, can the faculty please give the floor?
I mean, I like to say that at TIFR in seminars, there's only one difference between the audience and the speaker. It's that the speaker is standing.
You're going to say is that the audience speaks more.
Roughly same order of magnitude.
Sometimes that is also
All right, okay. So in this first lecture, I'm going to try to sort of compress 50 years worth of work that's gone into this understanding of the information paradox. So it's obviously not going to be complete. There's other things that we could discuss, certain things I'm going to skip. But if you're interested, you can always ask me later and we can talk about whatever. Okay, so let's get started. Let me start off by drawing the putative Penrose diagram of black hole evaporation. Informed some black hole by collapse of a star. There's Hawking radiation that comes out in flat space at Scry. Eventually, the black hole loses all of its mass so that at a later slice, the black hole is really gone. You're just left with some radiation. And the question is, and there's a lot of questions that come up in this context. So let me try to highlight what really the issues are. Okay, so originally Hawking did this calculation in the context of QFT on curved spacetime. So we're starting in the 70s here. And when you do this calculation in this formalism of QFT on curved spacetime, what Hawking essentially found was we can start with some sort of pure state on the initial slice. The star could be in some specific pure state. But when you find what the out state is here, you find that it's mixed. So pure state, pure in state go through a mixed out state. And so if you really believe QFT on curved spacetime, then this is a violation of unitarity. So if you think QFT on curved spacetime is some description of quantum gravity, this is in violation of quantum mechanics in some sense. Really speaking, it's not, because you could always say that when I start with this slice, I evolve to a union of this out slice and a remaining piece that stays inside. So the evolution within QFT on curved spacetime from this slice, the union of these two slices is really unitary. That can be described by a unitary process. But the problem here is that as seen by an external observer, so an observer could just start from outside and just stay really near the boundary. And for an observer who stays outside, they've basically lost access to whatever was inside here. And so as seen by them, if they were measuring this S matrix, like in the LHC or something like that, they form a black hole, let it evaporate, whatever they get. In hand, the thing that they get is a mixed state. And so in practice, they've lost unitarity. So there's no useful description of a unitary physics for an exterior observer.
Okay, that's how Hawking.
This is basically, I'm in the 70s right now. So I'm really going to go through this historically and say things as people would have said it.
Yeah, and also, I mean, at some point the black hole has evaporated. It's gone.
Yeah.
So all that's left, you might think, is the radiation.
So the people who would argue for something like information loss would say, oh yeah, but you forgot about this piece that was inside. Yeah, as seen by this external observer, it's gone in some sense. You have no access to it. But you might say, oh, well, the complete description of physics was including that piece that you traced out. So of course you've lost information. That was what people pro-information loss would say.
A variant of that was that maybe it finally goes off into a baby universe
Correct.
somewhere. So in that sense, it's not.
Correct. It's there somewhere, but in practice, you've lost access to it. And so the key thing here was it was important as seen by an external observer, you really lost the unitarity. So it's
Hawking, when the black hole completely evaporates,
yes.
You could have recovered the information.
According to this calculation?
Yeah, what Hawking said.
Well, I don't know, but I think like someone who would really trust QFT on curved spacetime, a lot of relativists, for example, would say that the evolution from this full slice is unitary as long as you're considering the union of these two slices. If you trace out this, then on this outside slice, you've lost information.
The black hole getting evaporated is like tracing that somehow?
Roughly speaking, yeah. I mean, it's what the outside person has access to. It's like tracing out this part of the space-time.
So if you just wait long enough outside, you gather all the energy, you get what you put in.
Yeah.
But then the outstate is not related through a standard estimate. In fact, Hawking wrote papers saying there should be a dollar matrix.
Yeah, according to the dollar. This matrix is what you call the dollar matrix.
In Strings 2001, he came and said unitarity is not a good principle.
Is that right?
Yeah.
Here.
Yeah.
I forget that talk, I should remember.
It's a cautionary tale. It's not good to get a Nobel, get too famous.
People will remember.
He did get a Nobel, right?
He did.
Yeah, maybe that's the problem. He should have given. So okay, good. So at this point, people often, I mean, there was some confusion around this literature. Maybe QFT on curved spacetime may not be a good approximation. It was not so clear what really was wrong with that, because all that Hawking really assumed was QFT on curved spacetime to the approximation that you can essentially approximate the quantum state near the horizon by the vacuum. That's really all he assumed. In any quantum field theory, if you go to short enough distances, any state would roughly look like the vacuum, and that's really all that went into this calculation to show that it's mixed outside. So somehow you would need some sort of UV effect which violates that. And one way to say this is the three things, the three assumptions that goes into forming this paradox, so to say, is unitarity of the S matrix. This factor I said, which is that you have roughly a smooth horizon, which can be also stated as the equivalence principle, which is to say that the horizon is not really a special place. So in the language of the equivalence principle, this is just like any other point in QFT, and so you should just find the vacuum when you go to short enough distance things. And the third thing is essentially black hole thermodynamics. So it's to say that the black hole is described by A over 4G degrees of freedom, so it has some finite entropy. And so when you, so basically black hole thermodynamics. going to be described by some,
Pratik, I don't know how chronologically you want to go.
Yeah.
But just to say, since I might be the only one old enough, at least by the early 90s when this was revisited in the string community,
Yes.
the general thinking was known that there's another ingredient which is local effective field theory.
And counting equivalence principle as roughly including local effective field theory.
Okay, I see. Akash, I'll just call you back in 2 minutes. Sorry. Yes. So, okay, no, the reason I'm saying is, so if you're going to cover this, then it's, I'm so sorry, but the reason is that the variant which, was very persuasive, at least for someone like me, was that you throw in one copy of a bell pair inside, right?
Yeah.
And, for a long time, while most of the energy comes out, you can draw these nice slices.
Yeah.
And, if you can do standard physics on those nice slices very far away from the horizon, then, you have a correlation between one copy of the bell pair and the one outside. Just if you're doing normal local effective field theory. So how can, that information, which is not coming out in the Hawking evaporation, suddenly come out towards the very end when you only have a black mass.
Right.
So, if normal rules of local effective field theory, then okay. All right, anyway, okay.
That's right.
So if you were just evolving along, because the formalism you're using is clearly unitary.
Yes.
Because it's field theory.
Yes.
The problem is that stuff bangs into that singularity and sort of disappears, right?
There is a problem around this point as such, but you could have said it a little bit before as well. Like Sandeep was saying, you can say
smooth slices.
You can draw nice slices which avoid that and just stay close to this thing. And there's only a little bit that you're tracing out. You could still say, as seen by the outside observer, you're just tracing out whatever is behind the black hole, and you still lose information. So in practice,
but the problem is that one of the part that was behind the black hole seems not to exist anymore at late times, right?
Right.
So if you would just keep a slice like that, there's no problem. Right. Because that part disappears.
Right. Eventually, it'll all accumulate and become this slice.
No, but but what I was saying was, if on those slices,
I totally agree.
Yeah, I mean, so because of that, one of the things people often said was maybe an out is when those slices accumulate, there's something funny that happens at that corner. And that's basically the remnant version of this thing, which is to say, maybe at that corner, all the entropy suddenly comes out when this black hole vanishes. And that's a separate option, which I'm not going to discuss. And
there's this final state projection idea.
That will get discussed. That will get discussed at some point.
Yeah.
That's actually relevant to a lot of things.
You won't discuss it, but let me just say that one of the reasons people hated remnants was because they thought that even extremal black holes, which stop evaporating, would have a huge amount of entropy.
Yes.
And then that led to all kinds of issues with pair producing them.
Yes.
But now with JT gravity, we know that the real answer is that they have zero entropy. So actually the remnant scenario should now be revisited.
Yeah, like what used to usually get said is that these things run in loops.
Yeah,
and then
they run in loops and they give factors of e to the s black hole, which is exponentially big and it causes all kinds of issues and all. Actually, at extreme.
But is it particular to extremal black holes? Like if you had near extremal black holes, they would still contribute similarly.
Okay, we should talk about it, but at least the idea was you have a black hole, it evaporates, and finally, let's say everything evaporates away, but something remains called the remnant.
Yeah.
Is this a viable situation? Right. And at least that would have then meant some kind of extremal setup. So I'm just saying there's actually a window to look into that. Just keep that.
Okay. Good. So for most of this talk, I'm going to assume that this is true. There's some evidence we have for this from AdS CFT, for example, that this evaporation is somewhat unitary. And these 2 points are what will get reconsidered at various points in this discussion. So there are other options here, like for example, information loss and is one of those options, but I'm not going to discuss them.
I think how does these 2 points affecting the paradox state?
Which point?
These 2 and 3.
2 and 3. This is really the statement of black hole thermodynamics. So it's basically that it has a finite entropy, it's going to evaporate in finite time, and all of that radiation you can just collect and try to compute its entropy. This is how it's getting in here. Roughly speaking, it follows the page curve. So if you track the entropy, it's just an object. You can think of it like people often like to call it a burning piece of coal. It's just some object with a finite entropy. So what has to happen as it evaporates is it goes up for some time and then eventually comes down in some finite time. So you can make this measurement at that finite time and the prediction is completely off. So that's where this is coming in. Equivalence principle, as Sandeep was saying, is roughly speaking the way Hawking did the calculation. So we're just assuming that local effective field theory is fine in this region, and Hawking's calculation just assumes local effective field theory being fine outside. That results in Hawking's calculation, which brings up the paradox. And it's only a paradox because we were assuming unitarity. So that's why, like, this is really post facto. I mean, this is how people have said this later. When Hawking said, he just said, oh, QFT on curved spacetime gives you this. Now, because we tried 50 years of trying to come up with a solution, people have tried to tweak different things, and roughly speaking, these are the three things that people try to tweak. Okay. Good. So now let's jump ahead to the 90s. So in the 90s, people tried, I mean, maybe a little off in years, but roughly speaking, people tried to operationalize this problem. So one of the discussions that happened then was, can we somehow make this a very sharp puzzle in the context of one observer who can do this experiment? Okay, so one of the things that was discussed was the so-called cloning paradox. The cloning paradox says, what if here I had some sort of diary in state psi, and I drop it into the black hole. Suppose you imagined that there was some magical UV thing that brings out the information so that unitarity is actually restored. From the bulk description, there's a copy of this diary inside. So there's a psi here, right? And moreover, there's also a copy of psi here because eventually this information is coming up. So whatever information you use to form that black hole is somehow there both in the interior as well as in the exterior. And so this is against quantum mechanics because what you're doing is taking psi and forming a psi copy in and the psi copy outside. And this is something that's forbidden in quantum mechanics. So there's no quantum mechanical process, even including some crazy stringy UV thing that happens, which can ever make that happen.
Because this uses these nice slices.
Yeah. Use the nice slices. This can all be made like much before this. Because as we see in this picture, the information starts coming back down at what's called the baseline, which is roughly when it's half evaporated. You can draw very nice slices at that point, which never go to this corner. You can always stay in a region where there's low curvatures everywhere. We hope that effective field theory works.
Could you draw one nice slice of this?
One nice slice would be something like that. Can be at really late times, but still pretty far from here.
So what's the paradox here? That
the paradox is if you imagine there's some quantum mechanical process. So people would say maybe there's some UV thing that makes this work or so on. Any quantum mechanical process would have to, if it's consistent with the interior description, just the fact that this thing fell in, and the fact that the information comes out somehow, it would have to violate cloning. So there's no quantum mechanical process which can simultaneously achieve both. So the key point here is, and the way.
but here, I mean, no one expects that that's. I mean, meaning this paradox says you either recover it, or it is lost.
I would say until the cloning paradox, I'm not sure actually historically, maybe Sandeep can say, but I think people were trying to have both. I mean, without cloning, there's no real argument that that couldn't have happened. Maybe there was some problem
it's still there. The way it does not come out, this paradox stands. There's extra paradox here. If
extra in the sense, so here, like the calculation was assuming that the page curve can be computed exactly using just local effective field theory. Now, I think the statement is, suppose you're adding in new degrees of freedom so that there's some mechanism at the horizon, let's say, by which these degrees of freedom are getting transferred so that the information is really coming out in the outstate. It would have to come at the cost of that information existing in the interior. That's what's happening. So if you said an infalling observer just falls through smoothly just with this diary in their hand, and still somehow there's some quantum process by which the information comes out, that would be a contradiction with any sort of quantum mechanical process.
So if the semi-classical Hilbert space on a nice slice is a good approximation to the true Hilbert space,
Correct.
then it's impossible for information.
That's the point, yes. So what this is basically trying to say is that essentially QFT on curved spacetime could not be taken literally in this picture, like even with some extra effects and so on. One way in which this was said, let me say it in this way. So now we're going to discuss a few options. So option one is what's called the firewall scenario. The firewall scenario is basically the thing you might expect from just from unitarity, in the sense that you want the thing to follow a page curve. It seems like it's hard to have this interior description because of this cloning paradox. I want it outside, so I have to give up on the thing that's inside. So I just drop everything that's inside. I just think of the black hole as some sort of membrane which lives somewhere here, just outside. And then this is some hot object which is just radiating constantly. I form it and it evaporates. There's no problem with having unitarity for that. There's some complicated dynamics of this yellow stretched horizon thing, which radiates unitarily, and it would just be like a piece of coal in that sense. So the contradiction is really when we want to have both the in state and both the in part and the out. So here what we're doing is just giving up on the in part.
That we just so this has to be on the horizon, this line.
Yeah.
Because if it is inside, then you could have that paradox on the outside there.
And there's another option which is related to this, which right now won't be so relevant, but it will come up later. So let me just say it for now, which is that somehow the interior is not described by A over 4 degrees of freedom. This won't be, this will come back later, so let me not say much about it right now. But the third option that was interesting and that came up in the 90s and was arguably the favorite of a lot of people is this idea of complementarity. And complementarity was the idea that let's somehow try to have both. Obviously, it can't be done literally, as Shiraz just pointed out. If you take the picture of QFT on curved spacetime seriously, then you can't have it just because there's this cloning paradox. And so the key idea of complementarity was to try to operationalize this. So somehow try to only ever describe things that a single observer can. So normally we take this QFT on curved spacetime picture very seriously as what's happening in physics. And the idea was, let's be more minimal about physics. Let's just only ever try to describe the causal patch of one single observer. So you can either try to describe the physics of an observer who stays outside forever. Their description is just that they never access the interior. They only stay outside. They get all this radiation. They can check that it's unitary. That's all that they can do. There's also a person who can just fall in and they would just see smooth physics going through the horizon. As long as you're not trying to simultaneously describe both, then at this point at least, there's no issue. You can try to do smarter things and try to test this. So one of the things that people tried to test was, let's say you start collecting the radiation from this black hole for a really long time. So from the start of the page curve, you start collecting it for a long time. And at some point, you jump in. So you can try to collect some part of the radiation and then jump in and so on and try to see if there's a cloning paradox ever. And essentially what people computed in the 90s was, if you just estimate how much time that takes, you're basically too late. So if you try to throw in this diary and then wait for its information to come out in the Hawking radiation and then jump in, you're basically too late. You're never going to meet the other copy of the diary. So as far as it seems, from a single observer's perspective, there's no contradiction. That was essentially the idea.
It takes too long for the information to come out.
Exactly. It takes too long. This is some really large amount. And by the time you try to do that, you can also imagine a more sophisticated version where, say, Alice jumps in with the diary and then sends in information along the horizon to Bob. Bob collects a lot of this radiation and tries to jump in. Bob jumps in somewhere here, like when enough of the radiation has been collected. And then you can basically see that the energy of the signal that Alice tries to send is Transplanckian. So there's no EFT process by which this information can be captured by a single observer to see a contradiction. That was in the 90s.
The time it takes for the information to come out was a log of.
That's actually much later. That came with Hayden Preskill and so on. But
Okay.
at this point, it was like polynomial engine. So it's pretty big. It was like not even close. Okay. Okay. So the central point of this thing was that somehow we shouldn't take the full picture of QFT on curved spacetime seriously. And instead,
I need to add one more option just to ask you, which is fuzzballs, or is that?
yeah, that's another thing. I'm not going to discuss any of those other options. There's a lot of other variants of this violation of local effective field theory, like non-violent, non-locality, fuzzballs, etc. I'm not going to discuss
In
any
some
of them.
sense, fuzzball is like option one, right?
Roughly speaking, yes. I mean, it depends. Like people try to say fuzzball complementarity to mean, oh, it looks like a fuzzball, but when you jump in, it still seems fine.
There is a.
That's why I don't know if it's consensus.
What-
If
when you jump in.
it still looks fine, like as for
Looks like a
it,
black hole.
it looks like a black hole. It's like this, you fall in smooth.
You experience it, right?
You don't get
like-
fried. You don't get.
Yeah, you don't get fried.
Somebody will say you don't get.
So I'm not sure if the fuzzball community has consensus on whether it's this or this. So
And the argument against that was always, well, then there's an effective description in which you have all the paradoxes.
that's right. That's right.
In which you have all the.
Paradoxes of the black. If you experience.
They had some, anyway, that's not right. I'm not defending it. Yeah.
So I'm not going to discuss that.
And then just to say, I mean, the complementarity would have meant a huge breakdown of local effect.
That's right. So if you take
So we could be crossing a horizon right now and suddenly, yeah, I mean,
Well-
for all we know, I mean, the guy, it's not a local, the trapped surface is not even a local.
yeah, but complementarity, you won't see it as a local observer, right? There's no violation you see as a local observer.
No, what I mean is normally on such slices, we believe you can do local effective field
Yeah, that is totally
and
wrong.
so on. But, the moment you have such a slice, but it crosses a horizon,
Yes.
you can't have both. You have two descriptions now. The bell pair must both be entangled and not entangled.
That's right.
So that's like quite radical.
You cannot know it.
So
You
let me-
cannot know it, but I mean,
Yeah,
you
exactly.
believe, that this is the way you do physics, and suddenly, only in the far future will you say, oh, because they would bring a singularity, I would be crushed.
Like just to say this in other words, like the QFT on curved spacetime description cannot literally be true, as you were saying. Like you
Yeah.
cannot take that picture literally. But the interesting thing that came out of this was to say that somehow as long as you're trying to describe one observer who's just describing physics in their causal patch, they never encounter
Absolutely, that's the compliment.
and that's why like we could be going through a black hole and we wouldn't even notice. That's why it was so interesting.
Exactly.
It was trying to give you both.
No, that's right. So the
And-
word was or not and, right? You can be inside or you can be outside.
Yes,
But
yes.
you can't have a description for.
Yes. So the description in this case, like it was kind of an interesting proposal in that the description of physics was very observer dependent. Like you would it's not just standard QFT on curved spacetime. You describe it depending on which observer you're trying to describe. This is something that has resonated of late, and so that's why I wanted to make this point, because recently there's been a lot of discussions around observer rules and so on. And it sort of is in this spirit where the rules of physics sort of depend on which observer we're talking about. But as long as they can communicate, they should get consistent answers. That's all you should really expect physics to be.
And this whole island thing is some version of this complementarity.
Yeah.
Yeah, I will say how exactly it fits into that, but I would say I'll call it complementarity star or something. Like it's basically a version.
So that's a little more detailed, but basic idea was correct.
Yeah.
Refined version of
Yeah.
that.
I also feel that, although let me say that when I said this to Juan, he cannot really press it anyway.
Which thing?
The islands are a version of complementarity.
Yeah, I think it's
Argue against it.
Sounds.
it's not strictly speaking like
I see, okay, you
Yeah.
tell us.
Yeah.
So it's basically.
Are we saying that if two observers cannot communicate, then cloning paradox is no more valid?
Yeah, so the smartest thing you can, so obviously, as I was saying, there's two obvious observers you can draw here, one who just fell in with the diary and one who stays outside. And there's no cloning paradox for them, obviously, because each of them sees one copy, they don't see the other one.
Yeah, but at some point you would have made clone, is it like that?
Yeah, that's the thing to test is what if you stay outside for a really long time and then decide to jump in?
Yeah, but
So-
that can't.
Yeah, so if you try to collect the outside piece and then fall in and then see the inside piece, the test was you can't do that and you can show that you can't do it. So that's why there's no issue.
In that situation, cloning paradox is no more relevant, right?
So it's still a paradox in the sense if you take QFT on curved spacetime literally, then it is a paradox. So the point is that you shouldn't expect that QFT on curved spacetime is a literal description. Somehow all you can describe is whatever happens in one observer's causal patch and that's it.
That's what complementarity.
That's the idea of complementarity.
I think you'll probably come to this, but
Yeah.
as part of the AMP's criticisms, and
Yeah.
some of them maybe don't stand, some stand, but anyway, the original idea you're referring to, which was due to Preskill and then refined in Preskill, that if you try to gather information and fall and you're too late. This was, at least I remember talks by Wolczynski saying, no, this is not true. I can slow down things, I can speed up things
Yeah.
so that actually you can gather, you have enough time to gather the information and fall in. And I didn't follow all of that, but
Yeah, I'm not sure, because by the time we got to the fireball paradox, there wasn't that much discussion of this thing.
okay.
And I think, similar things have been said, but I don't think there's a very sharp situation where you can really make that happen.
Thank you.
When you try to make it happen, often you find that there's something like the Transplanckian issue. You try to receive this message and you find that there's some sort of Transplanckian type issue so that you can't actually do it within effective field theory and seemed consistent until AMPs.
These talks were after AMPs or before?
During
No, this is-
during the AMP.
I'll say something about that.
In what sense the island is like complementarity?
Sorry, which thing? So here,
Island.
oh, I'll get to that. We haven't talked about islands yet.
It's okay. But just to say, it's just that there isn't a Hilbert space with independent degrees of freedom here.
That's right.
Yeah.
So if there isn't, then that basic picture of quantum field theory of this nice slice is totally wrong at some fundamental level. And the cloning paradox was
It's like identified.
it's duality.
Right. And I'm really, really sorry, but the reason why I found islands to be much more dramatic was that the one thing beyond complementarity in islands was that you could actually manipulate the information inside
right.
from the outside.
That's why I say it's not quite complementarity, it's a super version.
So I
of
agree, and it's a much more revolutionary idea. I mean,
It's weirder than complementary.
it's much weirder.
It's much
much weirder.
and we should be bothered by it.
Yeah,
That would be the point.
And here in complementarity, things can happen there and outside separately.
I'm not exactly sure what they thought. I think they thought there's really nothing you can do outside which will, I don't know why, but yeah, I think they really thought there's nothing really you can do outside to spoil the description of the interior observer.
So who thought
In the 90s, I think that's what they would say.
Yeah.
it would actually.
Having lived through even participate, let me say, I mean, the general thinking was that this is like the Heisenberg kind of answer. You have the inside or the outside.
Yes,
Whatever you do outside is a complementary description. You're going to just the interior.
that's right.
It was consistent with two kinds of observers.
That's right. One of the things that was said then was that somehow they're like non-commuting observables, right? Like you can't simultaneously
Heisenberg's
so then, in that sense, if you act on the outside,
Yeah.
it's non-commuting, so it would act inside. So I feel like they should have thought of this, but that was not the spirit of the era. So they thought it's all consistent. Like one way to think about this is, as you were saying, like they're secretly the same degrees of freedom, and the way people said
That's
it
the island point of view, right?
Well, that's the complementarity point of view.
Well, I thought complementarity would be that, people fall in and people also go out, right?
Yes.
And then things can happen differently inside and differently outside, right? But it's not, it's not like one in some way identified with the interior. The outside.
But you don't want, in doing
It's
so,
just that you have consistent description on both sides.
but in doing so, you don't want extra degrees of freedom, right? Like you still want to describe a black hole.
Well, as long as you just want to describe the experience of a given observer,
Yes.
I thought that's the only rule.
So
Because you already broke down this effective field theory on the slide.
I guess it depends on what's the description of fundamental physics. So
Okay.
certainly we're fine with some A/4 degrees of freedom as seen by the exterior observer, right? They can collect all this radiation, it's just in their hand, they can do whatever. Now there is some other infalling description, and the question is, where is that in fundamental physics? What they're trying to say was, okay, you can effective field theory is fine as long as you're trying to describe just this causal patch, but somewhere it has to sit in fundamental physics somewhere, right? So the idea was they're secretly part of the same degrees of freedom. It's just some scrambled version of that. So in this sense, it's non-commuting observables because it's the same degrees of freedom there and same degrees of freedom here. And so if you act here, it should act on the interior in some sense. It's just that it wasn't ever relevant because you only were ever trying to describe the physics of a single observer. So it wasn't a relevant question that year. There was no, yeah. But this issue is going to be an issue because we have amps and amps is exactly this issue. So we're still in the 90s. Go ahead, skip ahead a few decades. And basically, I think maybe Sandeep can tell me, like, I think this was basically the norm. Like, this is what people accepted as what's going on.
Well, I don't know. Let me just add
Yeah.
one more small thing. Sorry.
Yeah.
Which is that also the other thing in the 90s was people tried to solve explicit 2D models.
Yes,
Okay.
and there was information loss.
Yeah, where they showed information loss, but let me just say I myself participated in some of that, but the one solvable model was actually not CGHS,
Yes.
but the RST
Right,
model.
right.
And some of us spent time, but after the string theorists withdrew, Ashtekar, along with, this guy who did the instability on the one extra direction, numerical relativist. Pretorius. They wrote a paper, which, by then the string community, they wrote a paper solving the RST model very precisely numerically, claiming that it had remnants as the answer. Okay. And I just feel like it's worth going back to a serious study of the 2D models, okay, with asymptotically flat.
I think there's a sense, there's a sense in which,
Okay, not asymptotic AdS, which is what was done more recent, but where you can actually hope to define an S matrix and see what. I just wanted to flag that issue.
There's a sense in which the islands are going to be like remnants if you interpret it appropriately. So that's this calculation, and you can try to make sense of that. Yeah. So now we move on to the 2010s, which is the era of the firewall paradox. And the paradox, I mean, the setting was similar.
The difference between islands and remnants is that if you had a remnant, then you would really see a mixed state on the outside.
Yes.
Island you don't. So I thought it was very different.
It depends on what's the interpretation of islands. So there's multiple different ways to interpret islands, and we'll see what it'll become very relevant, like what you're saying. In some sense, it's going to be related to this option 2. I see. There's different ways to interpret it. It could be either option 2 or option 3, and that's going to be the whole game. Okay. So now we come to the 2010s, and there was this interesting paradox which was actually first discussed by Marcus, and the idea was, in some sense, it's very closely related to this cloning paradox. And the idea was, suppose information gets out, so you've collected some amount of radiation, let me call that C, and then there's these two modes, A and B, which are these Hawking pairs. So the process of Hawking evaporation happens by these pairs. One pair falls in, one pair falls out. They're entangled because of vacuum of the horizon. And let's say you're post-page time, so that you're in a period where the page curve is going down. If the page curve is going down, what must happen is the new mode B that's coming out is entangled with whatever you already have so that it's purifying it. So B must be entangled with C for unitarity. So B entangled, let me just say entangled with C. For unitarity. And on the other hand, B must be entangled with A for smooth horizon or equivalence principle. Okay. And all of this already assumes that there's a finite entropy associated to black holes. So this was what Mathur phrased. And of course, at this point, you could again wave your hands and say, oh, but there's no single observer who can see this. So let's just say complementarity. What's the point of this paradox? But the interesting thing that was pointed out by AMS, just Almeri, Marolf, Kulczynski, and Sully, was this is actually a contradiction for a single observer within their patch. And so the argument is as follows. You can collect all the radiation starting from the beginning of evaporation all the way up till this time that we're interested in. Then you can process this information.
Sorry, so the complementary description would be that A is entangled and also C.
And also, yeah, they're both, I mean, A and C are the same degrees of freedom, roughly speaking. So what's the problem? It'll be entangled. Yeah. So we wait for some time. Post page time, this paradox shows up. Now, what you can do is you're collecting all of this radiation outside. There's a huge amount of radiation you have, but secretly there's some one bit in your set of radiation, which is going to be the thing that's entangled with B, right? So there's all of these modes that you have. You can process it so that you've extracted out everything else and the one bit that is going to be entangled with B. That's the mode we can call C. And then you can do that and then jump in.
What is it?
You can process all of this radiation, extract that one bit that's going to be entangled with B, and then jump in. So now you have C in your hand. Let me show it here just qualitatively. You can jump in with C, and now you see A, B, and C. If complementarity was true, you would see A, B, and C in your hand. But that's a violation of quantum mechanics within a single observer's causal patch, because then you can never have two things entangled with the same thing.
Then I would have said, oh, but it'll take too long for you.
Good. So
that's why you would say, oh, no, it need not take such a long time. Sorry.
Yeah, we'll get to that. So suppose I can do this experiment. So this fact of processing this radiation and extracting this one mode is some process. Let's think of that as a black box process where I don't know how much time it's going to take. The question is, if you can do that fast enough, then you can jump in and then you can see it. So the space-time picture as such is perfectly consistent with this, as long as we're not putting in any extra constraints. So at that level, there was a paradox. So at least at the level of the local effective field theory description, it's quite plausible that you can.
Why is it a version of saying that complementarity can only work if you can't gather the information outside and follow it? Because then you have the information inside coming twice, the original and what you gather.
Right. But there what was happening was you were waiting too long, because for this particular bit information to come out, it would have taken quite long.
I see.
But here you're just, so the thing that fell in and formed, was there in the black hole and so on is like far inside at this point. But here you're just trying to access something that's very near the horizon. It's not like, so the issue here was,
I see.
Alice fell in and then she tries to send this information to Bob, who falls in later. And it's hard to communicate that information. But here what's happening is Bob just has this information in his hand. He doesn't need communication from anyone. There's no transplant here.
ABC, could you say?
Sorry. C. C is the, so I shouldn't have said Bob. So someone, C, is collecting all of this radiation, processing it into one bit, and jumps in with C. And then they just fall through and C, B, and A, like right in front of them. It's not like they have to receive a message from someone who had fallen in a while back.
I see.
And so there's no issue with this transplant.
The node is A
is just right at the horizon.
It's hovering at the horizon.
It's just at the horizon. Both A and B are at the horizon, and C is in your hand.
C is part of early radiation.
C is part of the early radiation.
So they have to have that first.
Yeah, so they have to collect all of the radiation
exactly.
and then jump.
And then jump, and then you will see that.
Yeah,
But that's supposed to confer the speed up, is it? That the fact that A is just hovering, I guess.
Right. So it's a smarter version of this, because here you could still do this process, but the issue that was failing you was you wanted to receive a message from that person who fell in before. And that was the thing that was hard. That was the thing where you could plausibly say, this is Transplanckian physics, we don't know what's happening.
Here it's
But here you got around.
Assuming this black box.
Assuming this black box, so we'll get to that. But in standard effective field theory, there doesn't seem to be any constraint that would stop you from doing this.
But this sounds like an obvious kind of, why did it take so long for it?
It's a good question, I don't know.
It sounds like one epsilon above what you were saying.
Thinking a little bit about entanglement.
Yeah, maybe.
That's the new part. To get a sharp this thing, you need this entanglement.
Maybe that's, yeah. And I have to say that all of this was heavily inspired from, maybe one of the things to say is, yeah, maybe that's the thing to say. So Hayden Preskill happened maybe a few years before this, and that was a much faster version of this. So what happened initially in this case was if you try to do this experiment, it wasn't even close. Like there was not even a chance that, maybe there's a factor here and there which can change things. It was just completely off. Hayden Preskill realized that there's a faster way to do this algorithm so that this bit can be extracted pretty early on. And then this experiment was at least tight. It was like just Planckian. Like when Bob tries to extract psi from the radiation and then jump in, Alice's message gets to him at just Planckian energy. Before that, I think in the 90s, people thought it was just not even close, like there's not even a chance. So I think that was important to make it tight. So I think that was an idea that was missing. Like it's hard to imagine how people would have done it without Hayden Preskill.
Did you use entanglement there?
Yeah, Hayden Preskill heavily used. It's a very quantum information-y idea. The idea being that essentially any bit is sort of easy to decode if you have sufficient entanglement. Like you can just pick your choice of bit and extract it, and it's pretty fast.
So sorry, just to say, I mean, a lot was made about the fact the small corrections theorem and not played and decide. But I mean, all that was more or less understood when you say, complementarity, the fact that small corrections don't allow you to get around the basic.
Yeah. I mean, in post facto, this is probably easy to say.
Just to say, is it, as you're saying, that the idea that the black box could work fast enough? Because to me, it always seemed nearly impossible to extract C from all of the Hawking radiation.
Well, that's where this quantum information thing comes in. So the things that Hayden and Preskill codified was, as long as you have entanglement, there is an in-principle process which can do this, right? Then there's a whole other question of, can you do it in practice? Which is where all these other criteria will come in, which I'll talk about. But the key thing was, this can be done if you know the laws of physics.
And fast, because...
not necessarily fast. Their claim wasn't necessarily about fast, but in effective field theory, we never put in like extra constraints on fastness or something like that.
Like Hardo and Hayden.
So I will just.
Then you can do it, right?
You can't do it.
Can't do it faster. So it's an exponentially complex.
Yeah. So here the idea would be that you collect all this C radiation, and find your B also.
Yes.
So the islands would say when you jump in A, it's already is not there, or
depends on what you did. Like if you extracted this, then A won't be there. There would be a firewall of the at least one interpretation of islands would say that.
I see.
Yeah. So Rishmi has had a question for a while, so maybe I should put it.
What I'm asking is this. So C will have information from early radiation of A.
C
there.
Will have information about A.
Yes. Early.
Yes.
But at least it should have that diary in order to get that information.
Yeah, so C will contain the diary in some sense, in some scrambled form.
It is taking long to get that information and then it is coming back. So how is it different from this?
So there, what was happening was, I mean, roughly speaking, the diary was a worse version of this experiment because you sort of dropped it in early on, and then after doing this processing, you're trying to go back and find it. And that's hard because what will happen is this thing fell in a while back, and then you can imagine an observer falling in with that and then sending this message. And that message gets blue shifted a lot, and that's why it's hard to receive that message. Here, you somehow just circumvent that by not even having the diary be early in time. Roughly speaking, the diary is just at the time you fall in. Right? Like so this mode that's inside is literally the mode that's just inside the horizon that's supposed to be entangled with the thing that's just outside. So you just fall in and you just see it. You don't have to wait for this delay so that there's this blue shift and you can't see the message. That's what happened in the original complementarity.
C will get information only if we know about the diary.
So here I'm not doing this version with the diary. All I'm saying is C has to be entangled with B because of unitarity, right? Because the next mode that's going to come up has to drop the page curve down further. And so it must be entangled with B. But B has to be entangled with A because in standard quantum field theory, that's how always like the vacuum looks. And that's the puzzle itself. So forget about reconstructing the diary at this point. I mean, it's related, but forget about that. now you have 3 bits, and this B bit is supposed to be entangled with both A and C, and that's a contradiction in quantum mechanics. That there's no consistent quantum state you can write down which this observer would see within their causal patch.
So is C just the next mode of Hawking radiation?
It's not. B is the next mode of Hawking radiation.
Okay,
C is like
no. Oh, it's whatever it was.
whatever was
exactly.
Yeah,
Whatever
it
it
was.
was.
Nice.
I see. So it was generally accepted that it could be done fast enough or whatever. Okay, we are coming to that.
Yeah, we'll get to that.
People did get very excited that now this suddenly, I mean, I didn't, my problem is I didn't see why people got so excited in 2010.
Oh, I
It's a
see.
new thing. But I guess I now understand that it's the fact that the modes were hovering and everyone
Yeah.
was convinced.
Yeah, it was crucial. Actually, a lot of times this is called the Mathur-Amps paradox. And that's fair because Mathur had the ingredients of this, seeing that strong subadditivity is somehow going to be the issue. But the key point was showing that it violates complementarity, because otherwise you could just complementarity it away, right? You could just say, okay, so what?
Yeah.
Just like the cloning paradox. And so I think the key addition by Amps was that piece, and that's why people were so excited.
Sorry, just to understand this thing. Unless you know what B is coming out, how will you know what is going to be entangled?
So this is all
How will
assuming
you
that you
stand
know.
at infinity and pick out the thing that the next mode is going to be entangled?
This is all assuming that this external observer is like an all-powerful quantum gravity observer who knows all the laws of physics in terms of the full S matrix and everything, like all the description of how Hawking radiation is emitted bit by bit at all times.
So she can predict what the next mode is going to be entangled.
Exactly what it's going to be at times. So without that, you can do nothing.
Wow, so
This is so far.
no, but C can just collect all the radiation until
Then you're too late.
oh
Then you're too late. Because then you're basically the black hole is gone.
So
So it's very important that you can do it like as soon as this mode comes up.
That's why in some sense it's not
Ah,
to do this operation.
So say again, so I understand Shiraz's point. The point is that the person who's trying to extract must know what bit is to be, a qubit is to be extracted.
Yeah, this black box experiment that I said of like processing all of this radiation and extracting that one bit that's entangled with what's going to come out next. That black box heavily relies on the black hole S matrix, right? It heavily relies on which mode that's going to come out next is entangled with what.
You should have to know what's going to come out next.
You have to know what's coming, otherwise there's never
Next
contradiction.
is B, right?
Is B.
so why
Yeah,
Your because how do you know you extracted that one bit that's
just keep on extracting? Yeah, I didn't understand what is the problem. It's just having all the radiation with me.
then you're too late.
This is
Because,
very much
I mean, essentially, like if you're basically
It's like almost impossible to do.
That's basically what Marolf-Maxfield said.
all the
Being the
oh no, but
next point.
yeah. But this is a bad picture because
Then I jump.
you want to draw nice slices always, right? So you want situations where all of these modes are really subplanetary. So you want them to be on a slice which is something like that, and where you can actually physically collect them and then try to jump in, so that it's still within. It's a process within effective Euclid.
Okay, but now I better understand why the complementarity people didn't think. They would say it's too. Try to make this happen.
Yeah.
It's too weird to know. We want to know what's the.
It's too hard. Actually, no. I mean, more or less. Okay, maybe I don't know it, but I mean, this wouldn't have crossed anyone's mind.
Yeah, this is such a science fiction thing. Like,
See, it's easier to say you have the Britannica inside. Let me try to, but this is really.
because you have to have set up a very well controlled initial condition for this.
Yes.
You have to know the Hamiltonian of quantum gravity.
Yes.
And sort of, it's like you're sitting outside the universe in some sense, right?
Yes.
Yes. But this is something we imagine can be done, right? If I solve string theory, you would have access to this Hamiltonian, right? And then it's still an in-principle issue, even if you solve that problem.
Yeah, possible. Yeah. You can do it.
Meaning somebody can do it.
Somebody can do it.
Somebody
Somebody can do it.
God can do it. God can do it.
Yeah. I mean, if like the question here is like in principle, if you could do that, could you still make a consistent description of the bulb, given that? And the expectancy seems to be that
It's like that. It's a
yeah, I mean, if you only ever cared about effective field theory or something like that, then I guess, I mean, most of these paradoxes really assume that you can really compute the S matrix, like black hole S matrix, right? I mean, even computing the page curve is a relatively challenging thing to do in practice. Like, I don't know if we can ever do this in our lifetimes. But it's a pretty challenging experiment that you want to do, where you have like a huge number of degrees of freedom, and you want to see if they're
Microscopic.
it's a microscopic thing where you want to check whether it's unitary or not, right? Like coarse grain entropy is all perfectly consistent with black hole thermodynamics. So you really need to, somehow put in that this is in conflict with the existence of a putative unitary quantum gravity theory. That's where they should go.
Yeah, but sorry, there's one thing to say that there exists a unitary.
Right.
Another thing to say, to make the paradox, I have to know exactly what it is.
Okay.
That is another level.
Yeah. So Pratik, can you point out this distinction between if I was able to collect a single guy which is going to be entangled with B, how am I not too late? And if I do collect all these things,
I mean, basically because you have to. I mean, it's a little hard to draw on this picture, but roughly speaking, the relation
setting up of it.
is so if you add enough of these modes, you can roughly jump in within a scrambling. So when I process all of this here and fall in, the delay is
up there I can never go in, right? That's the space.
this picture is kind of very hard to draw.
No, but we should be just matter of drawing the line, right?
Yeah, I mean, then I would draw similar to what you were drawing. But it's hard to put in the numbers there. Right? That's the confusing thing. So, I mean, you will be somewhere here and you'll collect some of that radiation and fall in here, and the mode is secretly there. But there's a big amount of time in that region. There's a big amount of time here. And there's a big difference between being right at the end of evaporation when you've collected everything, which is when this process becomes simple. Okay. Because you have the full state and it's relatively easy. It's actually much more challenging to do it before. But that's when you can actually fall in and do it.
Now, Pratik, since you're doing such a good
But with 50% probability, can I be successful?
No, I don't think so. I mean, 50% probability being successful in what?
I collect half of the radiation, not full.
That's fine.
And then
But
fall in. Then the 50% chance I will encounter A, right? Which is
it's not okay. This is another point. In principle, what we knew was that there's some bit in this which is entangled.
Yeah.
Right? So why don't I just take all of it and jump in?
No, all of it you said is too late, right?
No. Collect all of the radiation at this time.
Yeah.
Like so.
But that's what I was saying.
Yeah. So
That's
let's say I've collected 60% of the radiation.
Yeah, 60%.
And I forget about this processing and extracting a bit.
Yeah, forget it.
Then there's too much back reaction because now I have a huge amount of radiation. I'm trying to fall into this black hole with all of this radiation. That's just going to form a bigger black hole. I'm never going to be able to form this paradox. The paradox really is when I'm able to extract it into one bit which doesn't have much back reaction and then jump in.
But let's say I collect that 60% radiation, but I still have to find that.
You still have to find that bit with good fidelity. Otherwise, there's no paradox. Otherwise, it's consistent with strong survival.
Now, Pratik, since you're doing such a good job, let me ask you one thing. See, at least for me, there was also the paper of Mallasena, written I don't know when, where he looked at just thermal AdS.
2001.
Oh, the AdS CFT paradox. Yeah.
And then he had a version where, he said, look, if it were really true that things were thermal, they would decay, but of course it can't be. And now you have the black hole, you have also thermal AdS. And what it alerted people to, morally speaking, although he didn't address the information puzzle directly, was that you should sum over topology.
Yes,
right. I feel that was sort of very perceptive, just to say. But then to add to that, there was this other thing that Mathur actually really said, which I feel. Which was, he said, look, you might think that non-perturbative effects are suppressed.
That's where the small correction
e to the S number of states, for a black hole, maybe that suppression is smaller than you think. That's also, I feel, kind of, I don't know, a rather perceptive remark.
That's related to this fact that that's where the small corrections theorem came in, which is the statement that these two have to be entangled with each other. And the conflict of that with unitarity is something that's robust to such e to the minus s effects if you want the horizon to be smooth. So just to say that in different words, like you can say that there's some e to the minus s's that show up and some corrections and so on. But if it happens in a way that violates the entanglement between P and A, then you've lost smoothness of the horizon. So he was not trying to address complementarity. He was trying to address this sort of an issue. And he was saying that it's not so easy to say non-perturbative effects save the day, is what he was trying to say. And then Andy said that's even in conflict.
Okay, good. Thank you. I mean, in retrospect, it sort of suggests that, maybe we should have taken different topologies most.
Yeah, absolutely. And I think what's happened recently is we've learned how to take them more seriously. That's going to be a very important thing. So at this point, then again, we were down to similar options. You could always just say firewall. So firewall you should think of as like a null hypothesis. Like if nothing happens, then go back to firewall and say, we don't understand the dynamics of this thing, but there's no interior, there's some complicated thing at the horizon, which is giving out unitary radiation. Forget about it. That's still a big violation of known physics in terms of equivalence principle and things.
Similarly ugly hypothesis, right?
Yeah, I mean, it depends on.
Beautiful space-time picture,
Yeah.
equivalence principle,
Yeah.
coincidence of
Yeah.
So, I mean,
That's the thing with this thing. Like relativists would call this the maximally ugly thing because like you've lost all beautiful covariance and so on. But like quantum field theorists would have said information loss is the most ugly thing, right? Like,
physicists, then you've got a certain eye for beauty. Say.
No, but also they had no equations at all.
Oh, absolutely. So that's why I mean it's the null hypothesis. It's like whatever you have a proposal for, you should always compare with the fact that we just wave our hands and say we don't know the dynamics of this object, but there's something that destroys the interior. Then it's always like you should always compare with that as a benchmark. Like if you're doing worse than that, then you probably just fall to that. That's the
So Pratik, here, let's say I'm able to do that, and then I jump to the horizon, then I see the firewall, right?
sorry. If you do this experiment, yeah. So an experiment that you do here would have said. So the option one would really be the statements that the firewall was there all along. Like there was no A to start with. So there is no contradiction because there was no A to start along. If you follow, you would see a firewall. Yeah.
Without even logic, so whether I do the experiment or not,
independent of that.
doesn't matter.
Independent.
Because it's just my experience.
Yes. Independent.
So the island scenario is that you would see.
Yes. So let me get to the other options. The other option, so option 2 again, I'm going to leave for a little bit later. Option 3 is what I would call complementarity star. And the star is really putting in extra bells and whistles to make complementarity work. So the extra things that you're trying is related to what Sandeep was mentioning, which is you somehow want to put in a bound which would stop someone from doing this experiment. What could stop someone from doing this experiment? Now that we've seen that within effective field theory, I can do this and jump in, the only thing was this black box, which was processing all the radiation and extracting this one bit that was causing the problem. And so what was proposed by Harlow and Hayden, related to what Sandeep was saying, was there's a bound on complexity because this black box process is actually really hard to do. Even in principle, like it's if you had a quantum computer, it would take much longer than the evaporation time to do that computation to extract them. So this would then say that the reason this was a slightly strange or different version of complementarity was because what you're saying, effective field theory holds as long as you don't violate some complexity bound. So normally we just say effective field theory holds as long as we're at sub-Planckian energies and we don't have large curvatures and so on. Those are the conditions we put for when effective field theory should hold. This would be an extra condition you have to put to say that somehow you can't do two complex tasks. If you do two complex tasks, then you somehow violate standard effective field theory, and complementarity holds modulo that fact. So complementarity was saying for a single observer, your description of effective field theory is perfectly fine as long as you don't violate, you don't have trans-Planckian physics, etc. Now you just put in an extra condition that you also can't do two complex operations.
Can I ask you?
Can I?
Sorry.
One is to
There's only one complex task here. The complex task is extracting C from the set of radiation that you've already collected. That's the thing that you're really matching it with. So you want to extract C such that it matches with B. That process of finding exactly the thing that's going to be entangled with B is a very complex process. That's the only thing. That's the only complexity bound that's important. We can't do two.
Too much.
TW.
Oh yeah, sorry. Yeah, we can't do two.
Sorry.
Yeah.
So sorry, Ravi, but let me just ask you this. Suppose I don't want a new principle in
Yeah.
physics about complexity.
Yeah.
But I'm willing to take time, right? Like so now
Time is complexity.
no. But one thing is, but tell me, I felt that nobody quite tried to make the following precise. Okay, suppose something is so complex.
Yeah.
How much time would it take if everything can run no faster than Planck time? Each step of a processor can run no faster, or you're not going to consume so much energy that the processor will become a black hole.
Yeah. That is what was discussed in this paper.
Right.
Hayden is that point. That's exactly what they wanted to discuss. And
What are the gates?
No,
Huh?
I mean,
so complexity is robust to choice of gates.
Just use a full non-local unitary.
Yeah, I mean, it's always like locality. You always put in locality.
How long? How big?
How big?
Like how many qubits at once?
A few. I mean, it's order one. Like something that doesn't scale with numbers.
So that does not change this.
Yeah, these are always parametric things, right? It's either exponential or.
I thought this question remain unanswered in terms of whether you can actually build a quantum computer fast enough to do so much processing in the required time.
That's right. So initially what Harlow and Hayden tried to say was there's just no way to do it. So that happens
Based on what principle?
on complexity. So there's a black box version of this thing. So you assume that essentially the black hole matrix is kind of pseudo-random. So if it's random enough, then this process of extracting that bit takes a long time.
But don't you have to put some limits on your computational ability? How long it takes will depend on how powerful your computer is.
Right. So that's related to Abhijit's question, I think, which is to say that imagine I just have a quantum computer which stores all of this radiation, and I'm allowed to do local processes. So I act on 2 qubit gates or something like that. This is the standard thing in complexity theory. There's an arbitrariness in what gates I'm allowed to apply and at what rate and so on. But as long as everything is order 1 here, it's just a parametric statement. Is this exponential in the degrees of freedom or polynomial?
But now I want to turn it into a physics statement, which is I allow each step roughly to occur in Planck time, and I allow so much energy and so on. Is there a fundamental barrier to doing it which comes from the, nice to see that Planck. If I could run an arbitrary, let me put it like this, right? If I can run an arbitrarily fast processor, I can of course do it in the time required for anything, right? So it would be neat if the Planck time is on the boundary or if it's far.
This is really hard to make sharp because complexity theory is complicated. So people have tried to do this sort of thing. So already Harlow and Hayden tried to make some argument that this can never be done, assuming some sort of computer that works like what you said.
Okay.
Then AMPS came back saying that, oh no, there's a way to, it's related to what you said Polchinski used to say, which is you can slow down time by having some big redshift factor.
Yeah, that's what he used to say.
So it's a messy subject. Like I don't think there's a clean answer to this is the best you can do and this is the best way to do that experiment. There's different things that have been proposed, and I think this is something worth understanding, but it's a complicated thing to understand. Complexity theory is kind of messy. It's not so clear.
So this complexity is exponential, right? In the Gibson's constant. So even though I'm able to do computations very fast in right time, I will not be successful because that just
right. So that's doing it. That's if you were sitting here and doing it in some way. Then the proposal was, okay, maybe you can build some sort of more complicated geometry where there's a relative redshift between that region and some really further off region where you can try to do this. So you send this information there, do the processing there, send it back and so on. So it kind of gets messy because there's so many different ways you can try to do it. And there was not one sharp thing that came out which was the best. Certainly, if you just literally did this, stay here and try to do it, it's too late because it's exponential.
Here meaning within order 1 distance. So
yeah, just like let's say I was in flat space and stay at some really far distance, like as far as you want. You can't.
Like Sandeep was saying, what would be really cool would be to say that either to go so far that it takes so long to send your thing, or if you stay at a reasonable distance, there'll be a collapse process set in that. I mean, that would be sort of nice.
Right.
Very nice.
Yeah. I mean, it would be sort of tie that in.
Right.
And then this would not apply to the boundary field theory. On a boundary field theory, you'd be able to do whatever you wanted.
Yes.
Because that's just your own Hilbert.
Yes.
So it would be a limitation on what bulk observers could do.
Yes. This is very much a limitation on what bulk observers
and somehow would be in the spirit of what Subra says.
Yeah.
Since the last point again shows that on the boundary you would be able to.
Because on the boundary, there's no have another field theory or neighboring field theory. Do whatever. If you're a boundary observer, you can do anything.
Yeah. Like, I mean, roughly speaking, like in many of these island type things, you can just take the radiation, move it outside the gravitating region, do whatever you want as time here, then come back and, just fall in after that. So if you're allowed to go outside the gravitating space-time, you can basically do anything. Being on the boundaries, what is that? And so,
for one thing, there's no blank time. You can run.
yeah, you can do whatever. There's nothing.
There's nothing.
So you can do anything. If you're so one way, like I like what how Raphael likes to say this is the principle that would have to underlie this would be somehow that you cannot turn off gravity or something like that. You can only stay in this region where you have gravity, try to do things there, and there you can't do it. Because if you were allowed to go outside and stop time and so on, then you can do whatever.
Right. But what I meant was it would be really neat
Yeah.
if gravity provides the fundamental cutoff,
Yeah.
and then the whole thing is consistent.
It would be very nice.
But it's
Firstly, I don't think it's tight enough. As Abhijit was saying, like this is an exponential time, and it doesn't look like we have any exponential time here at least. Maybe in some other experiment or so on. I don't think this has been made as clean and sharp as possible.
But maybe the energy needed also scales.
Yeah.
The energy is really small because, needed, okay.
No, that's what I thought.
It could be that if you
You
try
have
to
to
do it
hold
really
it.
fast, then
Yeah.
you
Let's say
need
you
really
need a computer that has to hold all this information.
Yes,
yes.
No, that you can do because you can be arbitrarily far off and you have a lot of space.
But then maybe it takes too long.
Yeah,
That's right.
Then
So
for
there's an interplay between.
See, it would be so neat. You need some amount of energy to do it.
Yeah.
If you spread it out,
Yeah.
the computer has to talk to itself in the first place.
Yeah.
Etc. etc. If you try to concentrate it, the computer forms a black hole.
Yeah.
I mean, whatever. In various ways, gravity comes in, and then you just can't do it.
Yeah,
This
but
would be really cool.
this is something that I think was discussed a little bit around the time of the firewall paradox, mainly by Harlow Hayden and AMSS.
Okay.
The rebuttal to that.
Okay.
AMSS had a proposal for this thing where you don't stop time, but you really slow time in the way you were saying, where you have some large redshift and you try to do a process where you essentially send the information out, do the computation, and send it back in. It wasn't quite, I would say it was inconclusive whether that can actually be done, not done. It wasn't so clear.
Okay.
It comes down, yeah. So I think what people went with then was that, okay, maybe if there's complicated enough processes, you can do it in some way, but then you violate effective field theory.
And in the island story, just to ask now, if you try to do this experiment, the understanding is that will change the space-time when you do it, right?
That is one interpretation of it. Yes.
I see. Is there another? I thought
That is, that is one interpretation. I will say what the other interpretation is. Yeah.
How much minimum amount of radiation I will need to extract this information of B?
Sorry, can you say that
How
again?
much minimum amount of radiation I need to collect to extract the information of B?
Oh, you just need to be basically just past the page time, like a little bit past page time. Not too much.
So it will save my time of getting B, right?
That's why it was so nice. Instead you could have just waited till like the end for this information to come out and so on. That's too slow. The thing that Hayden Preskill essentially taught us was how do you do it just past page time.
There will be two things that were necessary for this to work, right? One would be this processing and extracting the C out.
Yes.
And the other is to know the S matrix of the universe.
Yes.
That is also complicated. That is probably.
But that you can imagine that you did it over like really long times. You evaporated e to the S black holes, figured out the whole S matrix, and then did this one experiment. So that you can't put a bound on that just from this.
But then you have to store that information.
Yeah.
Maybe that's hard to store.
But the information in that is just an e to the S by e to the S matrix, right? It's not like outside far enough, you have enough space. You can store whatever you want.
Right. But you have to go far enough.
You have to go far enough.
Yeah.
Yeah. Okay. Good. How are we doing on time?
We can have more lectures on that.
No complexity bound.
No, anyways, just totally great. Yeah, because all of us have got bits of the story, but it's been put together really nice.
This is the plan was to like basically lay this out, and so hopefully, if there's any.
It's really great, Pratik. Just keep going.
Yeah. Okay. So let's jump a few years ahead to 2019 to present, I guess, which is the islands era. And so different people would say different things about islands, which is why my answer to Shiraz has been so vague so far. So I'll try to clarify what are the different ways to say it.
Usually in physics, you don't have different people saying different things about.
I think that's right. That's right. And this is the main issue here, which is that we haven't found that one sharp. In principle, I think we should be able to formulate this sharply enough that we'll just have an empirical answer to it. At this point, a mathematical answer to it. At this point, I think whatever we have so far is consistent with a few different things, and then it becomes a little bit about your priors on what you're willing to give up.
You tell us how you can. I thought this PETS map and so on was very.
Yeah, I'll tell you why the PETS map is not that clear.
Okay.
Like it's not so obvious that that's
Okay,
fine.
What was the natural
Sorry.
complementarity star proposal?
Sorry.
What was the
Yes.
next direction?
No, at this point, complementarity star. Yeah, I mean, it's going to get related to this. But complementarity star was essentially to add in complexity bound.
So now
And say-
people who think are the ones that don't believe in stocks or people. Otherwise, they will just give up, right?
On complementarity?
No, on this, issue. That this kind of thing would be there also.
No, I mean, there's always the other option.
No, but complementarity star will hold, right? Always.
Why? I mean, that's one proposal.
Yeah.
Yeah.
So maybe you can continue.
Yeah.
I was just want to see what would be the way out of this.
Or the way out of this.
Yeah.
Okay, let's talk about it. So, and the other thing, I mean, there's related paradoxes that you can phrase in AdS CFT, for which you basically need something like state dependence. So these two things are essentially the starred version of complementarity, where it's, roughly speaking, what people would say then was that you can do this experiment and have it related to what Shiraz was asking. If you do this experiment and somehow go beyond the complexity bound, then you can just form a firewall at the horizon. Like you have by hand created something there, which is a highly non-local process. But it's outside local effective field theory because you broke the complexity. So as long since you've gone beyond what this new bound tells us about when effective field theory should be valid, it's fine that it's local.
Yeah.
And similarly in AdS CFT, the way to formulate this is that these operators that are behind the horizon are state dependent, and it's the same version of complementarity where you just say the interior is some scrambled version of the exterior. You can act on these operators in some complicated way to act on these.
I guess what I was asking, what would be the thought experiment that challenges complementarity star?
Complementarity star would be challenged by just doing this experiment.
Then as you said, you just had on the firewall.
So you may or may not, I don't know. What if you didn't encounter firewall, for example? That would be something else.
Sorry, Pratik, I missed this last comment. Sorry, complementarity star is islands, I gather?
No, not yet.
Oh, okay, so just once, I'm so sorry.
The complementarity star was just what I was saying there. Like after firewalls, the way to preserve complementarity, the best way to preserve complementarity would have been to add something like a complexity bound, like the Harlow-Hayden like bound, so that you say, if you violate this, then you've gone beyond EFT, and a version of that. I mean, all of these sort of converge to each other. They initially try to sound as different as possible, but they sort of ER equals EPR, Papadodimas Raju, A equals RB. They're all secretly the same sort of thing, where it's basically some state-dependent version where the operators in the interior are realized as some scrambled version of the operators in the exterior. You can act on them and act on the interior. That's sort of the idea. So that would be a souped-up version of complementarity, where it's not quite complementarity because local effective field theory in the naive sense is not valid anymore. But if you put in this complexity bound, then it is sort of valid.
But that is when you are allowed to do things violating the complexity bound, but
Yeah.
then this local effective field theory or whatever, you can manipulate the inside.
Yeah, local effective field theory is broken once you break complexity bound.
Can I think of AdS CFTs as some sort of extreme version of complementarity, where the field theory is like
Yeah.
part of space-time beyond infinity?
That's right. That's actually the way I initially thought of islands, and maybe some other people would have thought of it that way. So let me just say what the islands era brought us.
So complexity bound, as you were saying, is not made fully precise. Like
No, it's not fully precise. It would say there is a slightly more precise version of it, which I'll say in the context of islands. Roughly speaking, you shouldn't be able to do things that are exponential in 1 over G, where the relevant thing ends up being e to the S of the black hole. That's the relevant thing. Shouldn't be allowed to do operations of that kind. But it's not sharp, and that's going to be an issue.
Okay, I never thought of holography as complementarity. I thought of it as a duality. There were two descriptions. But tell me.
I was thinking complementary is very similar, right? I mean that either you've got the state in the boundary, or you've got the state in the boundary. They're the same state.
Yeah.
You shouldn't have a Hilbert space with both.
Yeah. I mean, the bulk is a scrambled version of the boundary is one way to say it, right? Like, you don't simultaneously try to ask about
There's no product Hilbert space or
Right.
boundary.
I think the difference is that we wouldn't raise a puzzle like this, right, in that context. Like we wouldn't say, can a field theory observer decode the pair, the sea and fall in, right? That's not I mean, there are two descriptions.
Imagine like you're like someone.
But some of the things are as weird, right? The fact that you can do something on the boundary and suddenly create a truck in the boundary.
That's as weird. That's as weird.
Yeah.
The non-locality aspect.
Yeah, the non-locality aspect is
What I was thinking of was that if you think of the space-time up to the boundary, and imagine that there's a space-time prime beyond it, and that's the field theory.
Right.
Then there's the description of space-time up to the boundary is in that space-time prime.
Exactly.
It's very vague, but in some sense, complementarity, but not just for behind the horizon, but for all of space-time. It's really not useful.
So no, a non-local aspect
Yeah.
is most dramatic in that.
The non-local aspect is dramatic.
And very similar.
And the encoding is very similar. Actually, that's right. The dictionary between the space-time prime, which is outside some region where you have all the radiation, to the thing that's inside, is roughly like holography. Right? It's roughly like AdS.
Inspired by holography.
Very inspired by AdS.
And so maybe what Shiraz is saying, you're saying is that instead of being so worried that I can manipulate the outside and suddenly get a bomb to blow up in the island region, I should just think of it in AdS space and be equally.
Yeah, you do a complicated operator on the boundary, and you suddenly create someone in the
These
boundary.
things are a big difference, right?
Yeah.
Like, that is not an exponentially, I mean, but by any standards, it's an exponentially complicated process. Here, there's an exponential complexity.
Here there is
Just AdS. It's vacuum AdS space, you can create a truck at the center of AdS by acting.
It's a little unclear what.
It's not.
It's not.
It's even causally, right? You can go back in
Yeah,
time.
so it's even more surprising, right?
But I would say it's actually the same because like it's roughly like what is the thing that controls how something is complex? It's e to the s,
Yes.
and s here is just 0. So like
Okay,
like,
in that sense.
yeah, it's kind of complex from AdS. Order 1 complexity.
How is it so easy to create a truck in the center?
You just go
Like
back.
you just do a complicated operation on the boundary. Like if you had HKLL, for example, you would write some operator in the bulk as some integral
So
over.
you go back
operator
and
on
turn
time.
on the source.
But you would have to do that. You would have to manipulate the gluons, not the gluons, right?
Yeah.
And that's huge Hilberts, right?
Yes,
Yeah, it's an order n squared.
Yes, but it's not, I don't.
Time, if you have to time reverse
I-
each n square gluon.
But it's not so clear, right? Because you have to evolve n square bits over some time,
Yes.
and that could add up, right?
But it's an order one. Fine.
Or order 1 time. Let's say every epsilon is something involving n squared. Is it clear then that it's not e to the power n squared exact? Because we've got a few Hilberts.
Yeah, I guess it depends on what's an easy operation. So if you think of the Hamiltonian as an easy operation, then I think I agree with.
Because we were time reverse, I'm just asking you, do we know how fine grained we have to make the lattice on the boundary theory to do it? Let's say it's on a volume V.
Yeah, you can make it fine grained.
But I mean, is it n square times V over epsilon, and how small does epsilon have to be? Precisely.
Epsilon can be independent of n for sure. So I don't think we have to worry about that.
Time reversal is because the second law forces you forward, right?
Yeah, even that's not so clear because we've got some chaos going on with these n square bits.
Yes.
Because of because in the second, you have to be very precise in time reversal.
You have to be very precise. You have to have a lot of control.
And it's a field theory, so there's a local degree per space-time point.
Yeah. But I mean, in all of these quantum computing algorithms, you're always assuming you have enough control over this quantum computer. Like, I mean, I think what you're saying is you have to error correct and so on. But we're imagining that we're a lab which is like precise enough.
I mean, maybe I was thinking of the field theorists who have to time reverse and Hamiltonian precise.
Yeah.
And it would be very careful.
Be very precise.
I mean, more than precise, like how many degrees of freedom do you have?
So you start with some number of degrees of freedom, some order n squared thing, which is
It's not n squared, it's n squared per lattice point.
Yeah. Like,
And how fine is the lattice?
I'm saying take it to be order 1, like some finite thing, not scaling with n2.
We don't know for sure whether it's in terms of radius of the space divided by the lattice coupling, how small the lattice coupling needs to be.
Let's say epsilon is just some factor of the radius. Nothing to do with
It's not
No, I don't think so. I mean, at least for the expression, the radius should be fine. Like, the UV is like some very near boundary thing. UV physics is some very near boundary physics. If you want to manipulate something deep in the bulk, then you don't really care about that. You can put in some cutoff which just excises out the near boundary stuff, and that's totally fine.
No, I mean, just in a field theory, if you want to time reverse the Hamiltonian, you have to time reverse all the degrees of freedom, right? So we don't have, the only way to know how precise the lattice coupling be is if you actually calculate this process. And then see how it scales with epsilon, right? In a strongly coupled.
It doesn't matter that it's strongly coupled. Like the fact that the Hamiltonian is something, whatever it is, and we're imagining that we have full control over that. Then it's a question of how many gates I have to apply to get to this thing. And then it's an order 1 amount of time.
But it's in that assumption that you have full control, because the real question is, if you're post-graining over some degrees of freedom, you'll have approximate control.
Yes.
Okay. And all I'm saying is, we would have to make a careful estimate of what that degree of approximation is with which you can get away. If you have to go some distance back in time, I think the further you have to go back in time reliably, the more control you'll need, because the system.
You can error correct.
Rise in the error correction. I mean, it's another way to state this.
I mean, what you're saying is true for all of quantum computing. Like, all of quantum computing is a messy process. Like, you may want to do Shor's algorithm on something. It's the same issue.
The only difference I'm trying to say is that if you had a circuit with some number of elements, right, it's one thing to make the estimate. When you have a strongly coupled field theory, okay, it's another order of complexity to make this estimate. Okay, and I'm not sure because you will replace that.
Do you believe that a strongly coupled quantum field theory can be simulated on a quantum computer?
But it's not a well-posed question the way you're saying it. Simulated with what?
To some approximation. To some finite precision, 0.01%.
I believe in an intrinsically chaotic system, if you have to reverse time, it's an exponentially complicated procedure. See, because the whole point about chaos.
I don't see why. I want by one time step, I error correct so that the error is 0, and then I keep doing it again and again.
Sandeep says that you have to get the initial condition really.
That's absolutely true.
So that's what I'm saying. So to estimate that initial condition so precisely, you have to pay exponentially complex price. No,
I think this is a different notion of complex that you're putting in, because here in quantum computing, what you're assuming is you have some initial state and you want to process it to a different state. And the question is how many gates I need to apply to do that. I can error correct at each step. So you can say my gates were a little bit off, but then I can try to correct that and do it step by step. So this exponential thing doesn't add up. And then it's an order 1 amount of time I have to evolve for. What you're saying is, can I even do this? Like is even this process? There's some complexity you're adding into it, which is outside this process, which is how can I get the initial state right?
You had a quantum circuit which was intrinsically chaotic. Suppose I gave that to you. Okay, you're running a quantum circuit which is intrinsically chaotic.
Yes.
Now let's try to make the estimate. See?
Yeah. I don't
usually we don't like to build quantum computers which are chaotic for this reason.
I mean, it's hard in practice, but I'm just saying that in principle, this process exists and it's not going to add a parametric scaling to the complexity there because of the presence of error correction, for example.
Because it's a chaotic system, just means that you can't then do it classically, right? You wouldn't be able to do that process on a classical computer. But if you had a quantum computer, you had access to the Hamiltonian.
I mean, it's of course hard. Like, we don't expect an experimentalist to do it very easily. Hard in the sense of experiment, hard in the sense of precision, but not hard in the sense of complexity.
So let me say one thing that Omkar explained to me that I find convincing. That is that suppose you're trying to create something your trunk is of energy E. Then you should be able to work in a Hilbert space.
Yeah, it's like a truncated.
Whose dimensionality is that of energy. Okay. Now, if we make that E very small compared to some reasonably small number, order 1, then you're working in a 1 cross 1, n cross m matrix, which is order 1, And then it's hard to see by n billion.
Yeah, that's right. That's right. Good.
I see.
Yeah.
I see. Is it, okay.
I mean, that's a truncation which looks very different from what you were proposing, I guess, where you have windows.
It was like very non-local.
It's a very non-local sort of thing.
It's very, very non-local.
But in principle, it's like, it's the same computation, like it's the same.
But if you think the field theory is all powerful.
Right.
I see. So you first understand the Hamiltonian villain. Okay.
Yeah, all of this assumes that you have actual.
No, okay, this. Okay, I was thinking of doing it the normal. Yeah.
What's last part of that argument?
Say you're looking at it, you're trying to create something whose mass is 1,000,000 in units of one. One is the radius of the state.
Yeah.
Okay, so it's quite a big thing, but it's not really back reacting. You want to create that kind of mini trunk.
Yeah.
Okay. Now you should be able to do it in e to the power million times e to the power million scale. Okay, but there's no n in that. Now you do whatever you do in time.
Yeah.
It's hard to understand how n will
Okay.
People compute the conformal dimensions up to 2, 3, and then you just imagine that you do billion times.
Yeah.
That's your millionth.
Just have the exact spectrum.
Yeah, we know how many scales.
Yeah, non-locally, I mean, just you diagonalize the Hamiltonian.
Right. Just compute all the OP coefficients precisely.
There is no lattice also.
That's it. Yeah. Exactly. Yeah. Okay. Good. So 2019. So there were basically two new ingredients that came in that helped shed some light on this, but still don't completely resolve everything. The first was the gravitational power integral. And it's related to what Sandeep was saying before, which was that somehow knew that this sum over topologies should be important to resolve some of these paradoxes. And in particular, the thing that got added in was these wormholes. These wormholes are essentially, and this was largely motivated from work on JT gravity, which is a two-dimensional model of gravity where we have a lot of control. And the idea was in that model, you have these processes where you have asymptotic boundaries.
So what is GPI?
Oh, gravitational path integral. And you can have processes which connect different boundaries, for example. So these are all different asymptotic AdS boundaries, and you can have geometries which interpolate between them so that they're connected. These are what are called wormholes. And in the usual AdS CFT literature before this, people often neglected these because it causes a problem, which is called the factorization problem, which is in AdS CFT, we would think about each of these as computing some partition function.
All this Euclidean, all this calculation.
Yeah, I mean, you can, like when people say Euclidean, it's like you can add Lorentzian sections and so on. So it's not like people often call it the Euclidean path integral, but there
What I was going to ask
Lorentzian
is that
sections.
because it's Euclidean,
Yeah.
I mean, at least I don't know how to make this relevant if the state depends on time at every time. I mean, there is no,
No,
let's
you
say,
can do this in
Z2 symmetry is important, right?
No, it's not. It's not.
Euclidean calculation to be relevant to the Lorentzian.
Yeah, so in that sense, it's not Euclidean.
Okay.
Like in JT gravity, you can just add Lorentzian sections and so on. People say Euclidean path integral to mean gravitational path integral sometimes, but if you don't mean that, then yeah, Lorentzian sections can very well be included. You can ask Schwinger-Keltish contours and so on. So it's not so restricted to be a Z2 symmetry. I mean, in fact, some pictures I'll draw one.
Okay, that would be very useful. Thank you.
Very good. So this is naively paradoxical because partition functions of the CFT should factorize. And this would be a contribution that is connected, so it's somehow not factorized. So this is what's called the factorization problem. And in JT gravity, this sort of makes sense because the dual theory is not really factorized. In JT gravity, the boundary dual is really an integral over random Hamiltonians. So instead of having a single CFT, you have an integral which is over, roughly speaking, many CFTs. It's just a random Hamiltonian. And there, these contributions need not factorize. So the interesting thing that came out of that was somehow we can make sense of these topologies in that context at least. So it was taken more seriously. The other thing that came in was quantum information. And in particular,
proposing that general resolution of this is that CFT that will go into gravity are some things.
I'm not yet proposing anything. I'm just saying why we took it seriously. It will be an issue and it will get discussed in the later lectures a lot more. So I'm not getting to that right. But it is important to highlight that this is sort of the problem in this region, like in this zone of things. It's very important to understand what's
So I think in the old days there was this Coleman puzzle.
Yes.
This was non-locality from Wolford.
So that's going to be very, very intimately tied to that. And the second lecture is very much going to be devoted to that. So we'll talk
Oh,
about
really? I see. I mean, that idea could never be made quite precise.
I would say Marolf-Maxfield is a precise version.
It's different. I think Coleman.
I think it's the same. Okay, we can talk about it in the next lecture. But that's going to be very important. Okay, excellent. And the second thing was quantum information, in particular, what's called the Hilbert formula. Trying to think about entanglement entropies that we're trying to compute more directly than. So what Hawking did was really get out this mixed state as an out state and then try to compute its entropy. And the interesting thing that was done here in this islands era was just directly try to compute the entropy without asking about what the S matrix is or what the out state is. And that gives us some mileage. So this RT formula roughly in this context would say the following. So we had this black hole which was evaporating, and we can apply this in AdS setups or in non-AdS setups. So one of the setups where people apply it is where you have an AdS black hole. And you attach on some non-gravitating region to it. So you allow all of the radiation to escape out. Then you collect it on all of this region, you call that R. So this is some non-gravitating region which is outside the original space-time that you had. So in AdS, remember that black holes are stable. So you need something for the radiation to escape out to so that this black hole actually evaporates. So that's what's being done by this process. And then you can ask, what's the entropy of the stuff that you collected in R? This is very similar to asking what's the entropy of some boundary subregion in AdS. So that's where the Rath formula comes in. And the answer is the following. It's basically that let me call it S fundamental. So the entropy computed in the fundamental theory is given by the effective field theory answer, minimization over I of the effective field theory answer of R union I plus the area of the boundary of A. So I is the island. So we can consider various different regions in the bulk. So what's going to end up minimizing this thing is going to be something that lies here. This blue region. And you notice that all of this radiation that came out here was secretly entangled with stuff that was inside because of the Hawking process. So there's modes here which purify this. So post-phase time, and by the way, so what you're trying to do is compute the effective field theory entropy. So just take the QFT on curved space-time picture seriously. So remember that for complementarity, we decided we weren't going to take it seriously, but now we're back to taking it seriously. Okay? We're going to take it seriously. And then ask what's the effective field theory entropy on R union I. So this thing is I, plus an area contribution that comes from the boundary of I. So the boundary of I is here, right? So roughly at the black hole horizon. And so this thing is roughly going to cost an area over 4G of the black hole size, the area of the black hole. And remember this curve was this way. The naive Hawking curve goes up this way. So the effective field theory entropy of just R, so if you didn't have an I, was this curve which is going up here. And on the other hand, the area of the black hole is shrinking. Okay, so the area of the black hole starts from some value and it keeps shrinking and it's eventually going to zero. This minimization essentially ensures that you follow the minimum of these two curves, which basically looks like the page curve. So for the beginning part, there is no I, right? So there's no island. All you do is compute the effective field theory entropy of R. But after the page time.
So what do you mean no I? That formula gives no I?
Yeah, the I that answers this is the null set. And post page time, it's advantageous to include an I because what's happening is there's more radiation that would have been entangled. That gets purified. So you win in effective field theory entropy. There is an area cost, but it's smaller. And so it's advantageous to actually have an I post-phase time. So That's the answer for what the entropy is, and this is computed by this page curve, and it very heavily uses these wormhole type things. So it's what's called replica wormholes, where the calculation goes as follows. You basically have
Just from a logical point of view, is it important that that blue dot there, which is right?
Yeah.
It will be distance away from the bright.
Yeah, it depends on the situation. So in this situation where it's just an evaporating black hole, where you have like transparent boundary conditions and allow it to escape to a bath, it ends up being that way. So as to not be a contradiction with AdS CFT. Like you could have formulated a contradiction if not. But there are situations if it had come outside.
No, I mean if it is all precisely at the present, that's it.
There are situations where it ends up being
like
precisely.
some mode escape or something like that.
Yeah, roughly speaking, yes. I mean, there's a slight delay in like which mode. So what this is going to say related to this complementarity picture is these degrees of freedom are related to what you already have. And there's a slight delay in you being able to extract that next bit. What is the thing you can extract given access to this radiation? It's at a slight delay. So the thing you're going to be able to extract is the mode that's just slightly inside, not the one which is literally there, just a little like a Planck distance inside. That's why it's a slightly big inside.
And then as you increase this more and more later, then this becomes closer and closer.
Yeah, I mean, it's roughly a Planck distance. I mean, until you have semi-classical control, and then it becomes tiny. And
So then you can control the entirety of the.
Almost like almost up to here, until it becomes a Planck size object.
So it's nice that there is locality also associated to time. How much this?
Yes.
You take this much region, you can.
Yes. This thing will move up roughly like as you go up in time here, it goes up in time.
And that tells you that there's some local theory. Inside the local theories.
Yeah, roughly speaking. Yeah.
Okay.
And now we are not worried about the fact that you can get the information in that region and then send it back in and do it.
We are worried about that. You should always be worried about that. And the version of that
complex enough. So I'm just.
So you could say that, or now here we've added on some non-gravitating spacetime, so we can just stop time and do things we like.
But I mean, it's more of a puzzle here, I feel, because gravity won't save you in that non-gravitating region, right?
Yeah.
So couldn't you do it really rapidly there and then send it in?
Yeah, and I will say something. Yeah.
So this is challenging the complementarity star proposal.
Yeah, we're going to have to say a little bit more than that. Yeah. I mean, it's roughly consistent with it, but
Yeah, maybe it's not a question, but suppose I don't take this big cost T and I take a large radius. Then still the island will create or no need to create.
Well, if you just have AdS, then the black hole doesn't evaporate.
Yeah, but I'm taking large.
So you mean like a small black hole in AdS?
Yeah.
Oh, yeah. If it's a small black hole in AdS, then it's roughly like flat space. So in flat space, there's a similar version of this where you just have this full region being gravitating, and you try to ask about the entropy of stuff you collected on some cut of null infinity. Then there's still an island for that. Is that what you were asking?
Yeah, then there will be CFT on the boundary still.
So in the case of the CFT, then the hard part usually is to isolate what the radiation degrees of freedom are. This is related to this Subrat's proposal of holography of information, which is to say that if you have a small black hole, all of the process can happen. You can form the small black hole, let it evaporate, etc. All of that is happening while it's still always a pure state in the CFT. Right? So the entropy never follows this curve. In the CFT, the literal CFT entropy just stays zero forever. And there's no page curve to be seen. But presumably, if you do the calculate, like if you extract out the algebra, which corresponds to the set of just the radiation degrees of freedom, not the whole CFT degrees of freedom, just the radiation degrees of freedom, that's going to be some coarse-grained version of the CFT algebra. That would presumably still see a page curve.
Another point is this blue curve is the collection of B, right? Initially there was this island.
Oh, this one? Yeah.
This
is what?
Capital B observers.
This is more like A.
A was outside.
No, A was inside.
Okay,
So
okay.
A was here, B was here, and C was here.
Okay.
So C is like R, and A is like I. So if you remember in complementarity, the idea was the interior degrees of freedom are some scrambled version of the exterior degrees of freedom. So there we were saying that A is some scrambled version of C, and here what you're saying is the I is some scrambled, like it's just scrambled and encoded all in R. Okay.
Pratik.
Question. Okay. Yeah.
Yeah. In that wormhole diagram, this below the GPI, below, yeah,
Oh, yeah, this one, yeah.
yeah. Is the bulk common to all these boundaries?
The bulk is common. So this is some bulk region, like some geometry, which has many asymptotic boundaries. So it's a bulk that's connecting all these different asymptotic boundaries.
Okay. But there seems like there is one. There are two diagrams here, two disjoint diagrams.
Yeah. So I was just drawing it for generality. So imagine you have AdS boundary conditions where you have 4 different asymptotic boundaries. So in AdS CFT, we set up the CFT path integral and then fill it in with the bulk. One possible contribution would look like this, where some things can be disconnected, but other things are connected.
Okay.
I could have just drawn a fully connected diagram. It won't change anything.
Okay. So the bulk will always be common to all these boundaries.
It could be, yeah. I mean, there would be disconnected geometries as well, but there would be some connected geometries. Is the point?
Okay. Yeah. Thank you. Yeah.
Sorry, Pratik, I really should know these replica things better, but just to ask you this, I mean, I thought the replica calculation was the souped up Ryu Takanagi to.
Yes, it's Ryu Takanagi. It's not even souped up, I would say. It's
Okay. And therefore pertains to the interior region. That is, you have the boundary of, so you have JT gravity, and you have a whatever boundary to that region, and then you do a calculation. Which is like doing Ryu Takanagi for the bulk, so yes, frame boundary, etc.
Yes.
From that to conclude that the region R outside, as the entropy it does, is the assumption that full state must be pure. Therefore, what is in the gravitational part, as captured by the boundary of the gravitational part, must, the rest must be outside. I mean, what's the logical, let me try to say it more precisely. Is it saying that, look, if the AdS region as measured in the Ryu Takanagi calculation can only hold some amount of entropy and the whole state is pure, then the complementary region must also have the same one. It's not a direct calculation.
We're applying Ryu Takanagi to not the CFT. Like we're applying Ryu Takanagi directly to R.
How are you doing it given that R is gravitational?
All R is so R, even the CFT is non-gravitational. But the point is like
it's not dual.
It's not dual.
He's saying it's not dual.
Not dual to gravity. That's right. So what we're trying to do is we set up. So there's a CFT coupled to this whatever quantum field theory it is. This Rath quantum field theory. Which is just some quantum field theory on the whole. That can be formulated as some path integral, right? So we can try to compute the entropy of some subsystem of that full system as a path integral. And now we're just applying the AdS CFT dictionary to this new path integral. So this is some Euclidean path or whatever, some CFT path integral, and then that sets up boundary conditions to be filled in by gravity. And that is dictated still by the original CFT.
This is a high dimensional gravity.
So here we can have, so there is some, so let's say this is D plus 1 dimensional gravity. There's a D dimensional CFT that's coupled to a D plus 1 dimensional QFT. And that combined D plus 1 dimensional object is a boundary to this D plus 1 dimensional.
Effectively,
dimension.
Sorry?
D plus 2 dimension.
No, this is D plus 1 as well, and this is D plus 1 as well.
Okay. Sorry. That's what you're saying about the R. How are you computing the entanglement of the R?
So yes, you can
say a statement of holography somewhere.
I think effectively extend the Ryu Takanagi proposal to say this part, it has no boundary. Meaning in the bulk, the bounding surface does not have to hit the boundary.
Yeah, you can say that.
It's effective.
Say again, sorry.
Normally, if we take some part of the boundary, we say the bulk surface has to be co-ordinate.
Yes.
Here, the bulk surface has to have null. Doesn't have that part. For the radiation. For the part that is, suppose you've got quantum mechanics and field theory. You do only the field theory, not the quantum mechanics.
Exactly.
Then the bulk surface should not touch the boundary. That's right.
So that's the picture. So this is the quantum mechanical system, which is this line here. Then there's the QFT, that's everything else. And we're asking the entropy about this. This can be formulated as a path integral. Okay. And we can use the AdS CFT dictionary to compute this by saying whatever is this green line, fill that in with all geometries and weight by the Einstein action.
So if you don't like this,
sorry, I mean this has to the fact that there is a particular region that you are carving out that has to inform your answer, right? I mean, if you just keep doing things at the green line, how does this lead us to that?
The way it does is we can prepare this state by some path integral, right? So let me do a two-sided version of this. So this two-sided version of this would look like this.
Yes, something like that. The state.
This is all the QSC, and this is like the holographic quantum mechanics in the QFT. And then to do the replica trick, we'll take many copies of this. So we glue it together. So we have this. We have another holographic thing. Right, and we're trying to fill in this. Like this middle region is empty right now, and we're trying to fill that in. What it will get filled in will be, and moreover, what we're doing is on the boundary we have some twist operators.
Yes.
And what's going to happen is the bulk gets filled in with disks which have twist operators as well, and the twist operator sits here. So this region is sort of swapped, and so where this location is a function of Rath. That ends up being the dominant contribution to these boundaries. And the reason it cares about this is because there's entanglement. There's entanglement between the holographic CFT and this path, and hence it is the usual aspect of this outside in some point relevant. So there's no one step less.
Sorry,
Yeah.
understand this step.
Yeah.
So we have let us say we have JT gravity in the
Yeah.
world, then the boundary theory is a quantum mechanics theory.
Yeah.
Now we are coupling that to a CFT.
Yeah, so quantum mechanics coupled to a 1+1 quantum field theory.
Yeah,
That's this. That was just this part of it.
Yeah. So how does JT gravity know about this part?
Yeah, that was also Abhijit's question. So what I'm saying was, here's a concrete way to see how that works. Imagine we prepare a two-sided version of this. So this is a path integral where this part is not filled in at this point. So at this point, I haven't filled in the middle part. I'm just creating a thermofield double-like state, which is where this green thing is like the holographic, like the quantum mechanical system, and there's entanglement with this. So it's basically the thermofield double for the interacting system, which is the quantum mechanics coupled to this quantum field theory. I take two copies of that and swap this region to compute the entropy, and then ask, how do I fill in this middle region? And the answer to that question is you fill it in with two disks. You fill it in with two disks, but there's a twist operator that's sitting here, so that this region is swapped with this region. That's what the island is here. So the island is this extra swapping. But roughly speaking, you just have set these boundary conditions and look for what the bulk gives you. And the interesting thing is these wormhole type contributions give you precisely the side.
And just to complete that, sorry, because you're computing it in the second Rennie for just the radiation, the swap operator is only acting on that eight-dimensional path.
Yes, it's just active.
But even so, the rules are that you should do whatever you want.
It's just
So you're allowed to.
Yeah, it's just AdS utility.
But still, see, so where? So one is thinking of this whole thing as a 2D geometry then? I mean, what is the bulk is trying to minimize some action?
The bulk is minimizing the action in this combined region, right? Like whatever is the geometry you fill in.
But why does it care about where this boundary to stop it?
It's because of entanglement. Like what's roughly going to happen is that action is going to get a cost from the area plus this. Like adding in twist operators will effectively add to the action by this amount. And sometimes it can be advantageous to have that.
Like it's not just the standard Lucas-Martasian thing.
It is Lucas-Martasian.
There is some entanglement that is important.
That's also Lucas-Martasian, like it's quantum extremal surface.
It's just the ordinary area minimization.
I mean, it's area plus, like the version of that which includes quantum corrections will have an AO4G plus S bar. If you minimize that thing, it's that. So it's it's just that it's still in the spirit of Lucas-Martasian. It's just that it's a different kind of situation where the quantum corrections are important, which one? It's not just area. It's just slightly different. Okay. Yeah. Okay, so the important ingredient here was this kind of wormhole which swaps a region in the bulk with another region in a completely different copy. And that's sort of inspired by this, the importance of wormholes in this JT gravity. And there's other things that these wormholes have helped us compute, for example, the spectral form factor and so on. I'm not going to say much about that. Okay. When do we want to end, by the way?
It's really up to you. You feel that there's a natural stopping point.
Yeah, I'm just trying to see if there's a natural stopping.
When will your historical review end?
It's another page and a half.
Well, I think the pace is excellent.
Okay,
So
okay.
I think we can have, like many lectures if you ask me.
Yeah.
But better to maybe.
I mean,
around one.
this is maybe a natural stopping point because, so, okay, let me maybe conclude at this point. So we will connect back to all the other stuff we said, but right now what we've seen is that the gravitational path integral computes the page curve. There's other things we can ask about it, which is related to the PETS map and so on. And we'll talk about that more next time, maybe, about how it is that the radiation encodes the interior, or does it, or yeah, what's going on. But what we've seen so far is there's a calculation within semi-classical gravity, which just computes the page curve. So it's so we saw that initially the tension was between unitarity, holography, and the equivalence principle. And this is just evidence again for unitarity being true. So I was not considering any options where I wasn't considering unitarity, and that this is just more evidence that unitarity is the correct answer in some sense. About the interior, we'll have to ask more refined questions to actually understand what's going on with the interior. And so that's, we can discuss that next time onwards. So for now, this is what I wanted to emphasize.
Let's see how do you put in how far along the page curve you've gone? That is, as this.
Yeah, that's a function of this region. So you can
see that one region size is.
The radiation is escaping there, and then you can fix which region you have access to. There's some amount of radiation which gets to that, so you're computing that.
So I mean, presented this review is one step leading to the other, right? So this there was this puzzle of ABC,
yes,
right, which was in some sense avoided,
yes,
by this saying that there is this complexity issue,
yes,
right? This which you call the complementarity star.
Yes, yes.
Is this discussion in the logical sense related to the previous one? If I ask that
at this point, no, I would say that okay,
ABC question.
Good. So
Is this going to offer a different answer than the complexity answer?
No, in some sense, no.
Better position.
Yeah, in some sense, no. This is going to be consistent with complementarity star, in the sense that so far what calculation I've described is just the page curve. So this at this point we haven't even phrased that question. Yeah. But if we try to ask the question that if I try to extract this radiation, jump in, etc., the answer would roughly be consistent with complementarity star in the sense that you have extracted this bit, so when you jump in, you have created this firewall, so you have accessed those degrees of freedom and spoiled the horizon there. You will see a firewall because you have created.
It's a more concrete realization.
It's a now we can do calculations. Yeah.
But actually, you can see quantitatively when the firewall is encountered, when it's not encountered, and so on.
Yeah, at least there's a proportion.
And then there is a you can see that it is correlated with the complexity issue also.
Yeah, that's the thing. The complexity thing got a little bit decoupled from all of this. People have tried to put it back in, and I'll try to emphasize that next time. But roughly speaking, its complexity here is being able to access. Yeah, no, I think it has been sidestepped to some extent. Like in all of these Euclidean, like the gravitational path integral type calculations, are sort of, you think of the complexity as, I mean, you're allowed to do this black box operation that you're trying to do. And
it's more about
if you can do it, then it will affect the interior. There's not been much of a discussion of whether a physical observer can do it or not. You can try to put that back in, but this calculation doesn't rely on
more of a how much of the radiation you are collecting.
Yeah, it's just an information.
Bit of a firewall you encounter there.
Yeah, it's just an
If you
information.
collect a little bit, the firewall will be small, but if you collect a lot, you will encounter big.
Not just collect, right? Do something.
Do something.
Do something.
You have to do something.
I mean, but collect also, right? Because it is inconsistent otherwise with that.
No, because you have to do some experiment in order to see that inconsistency. So that's why it was important to extract this one bit and jump in and so on. And what we are seeing here is that instead of saying all those words, you could have just said, I do this operation, and somehow the semi-classical gravitational path integral is consistent, if you have this dictionary from it, is consistent with just creating that operator in the interior. So that if you wanted to describe it in terms of an observer who did all of this and then jumped in, if independent of the complexity bound, like suppose they were magical enough to do it, then they would see a fireball.
But Pratik, I feel worried because you have a non-gravitating region that you can now really have an inconsistency.
That is why this thing is, it's not an inconsistency.
No, because the clock can run arbitrarily.
No, that's why it's not an inconsistency. And that's answering also Abhijit's question, which is that now the complexity bound has totally been sidestepped because you can always stop time and then do whatever you want on the boundary. And there's no complexity bound on this non-gravitating observer. But the answer to that is because you did that, okay, you're allowed to do that, but you spoiled effective field theory.
You changed the space-time, right?
Yeah.
It's like an AdS here.
You broke.
You do something which creates the total.
Yeah. So it's not inconsistent. It's just you created that.
Maybe you
But
can.
isn't there an issue if you let's go back to A? You see, there's a difference between creating. Let me just try to articulate. Let's go back to the original puzzle where you had A, B, and C.
Yes.
Right? Okay, so A was inside, B was hovering outside,
Yes.
and C was what you recreated from the Hawking radiation.
Yes.
Now let me take A to B in the eye.
Okay.
Right? Okay. And B it can be inside or outside, but in the
Yes,
region
yes.
which is securely,
Yes.
from the non-gravitational side of the
Yes.
gravitational system. Now, if I can decode C and jump in and meet A,
Yes.
then I've got two copies.
But you won't be. When you decode C, the operation will create a file. So this.
So for the you don't know this, but for the consistency, it would have to.
I know this PETS map would tell you.
Yeah,
It's
that's
like
not roughly.
I'll not.
I will get to that. I will talk about.
But it better work like that, huh?
That's. Yeah.
So you can, but I mean, it's too much to expect. You guys can actually prove there'll be a gravity. Can you prove
This
that?
one, just let me do this. So Pratik, is
I
it
mean,
that-
what are even the rules for creating? You can write down Armenian and show there's a firewall. You want there to be a firewall, otherwise you'll be in trouble.
One way to say this is that you just manipulate this particularly, right?
Yeah.
You can manipulate A.
Yeah. Once you can manipulate A, you can consider states which aren't entangled in the way you want for a smooth horizon, and so it must have a non-smooth horizon.
No, but I don't want to do that. I want a smooth horizon to create a paradox.
No, but there is no paradox.
If you measure this,
Measured it, then
measure and hold the C, you will create.
you spoiled effective field theory by doing that operation.
Effectively, you measure.
That's why you need complementarity star. Complementarity is doomed. Forget about that. Complementarity star is saying if you don't do things that are too complex, then all of these things are consistent. But you did something that was beyond that complexity, so you spoiled it. Sorry, you were saying.
So that's collecting C here. So collecting the radiation here and extracting C out, right? And that has affected.
Space like that.
Story, this better be true. I think, but are you saying that? I mean,
Yeah, I think you're saying that. I think you're right.
if I was skeptical, I'd say, you have to show there will be a.
So there are these path integral arguments, right? This PETS map, creating a PETS map through path integral. He doesn't seem to believe it so much.
No, I'm agree. But I'm saying it's too quick sometimes.
They prove there is a fire.
I
I mean,
No.
tell me next time. Tell me next time.
But can be shown using similar arguments to the Sluta-Kainagi or Dukovit's last. So you can unitarily manipulate a qubit inside the island by acting with some unity on the radiation.
Yeah.
Now that violates semi-classical effective field theory of the black hole space. So that's and then the complementary star will say that such operations are exponentially common.
Yeah. That's all. That all.
And so it seems very reasonable that if you were to distill C and then you would have to compute it, you would create a firewall because of very small.
And you can probably even show that from path integral.
That's- I think
Yeah.
basically using the same arguments, but applying Lukovitz policy.
Of course, it's all a bit fundamentalist. Because you're doing principle stuff.
Oh, yeah.
Since we went down that road in the first place, I'm just saying it better be the case.
Yes, I mean, if that wasn't true, then this won't. There's no use of this, right? I mean, it's only helping you if that is true.
Yeah.
And there is a consistent story, seemingly, we can tell you where complementarity star makes sense because of that.
And tell me once again, complementary star was what? If you do very complex things.
All the same statements as complementarity, which is you can have consistent descriptions of unitarity, equivalence principle, and S equals A over 4G for a single observer in their causal patch, as long as local effect, as long as they don't do things that are too complex.
So is it important from a logical point of view that the encoding map from R to whatever that is complex?
Yes, it is important for this complexity thing. It's not important for, I mean, if
this could just be that I do a simple computation and encounter firewall.
yeah, if it was that, yeah, if it was that, then you would see a, like it was related to this complementarity stuff, which is you didn't even need to do a complex operation and it would still get violated. Then the question becomes, what are the conditions under which local effective field theory is even valid? Like what constraint do I put in so that it's valid? Otherwise, everything, all hell breaks loose. So you need some constraint like that. And in plausible models, it is true that it's complex.
Right, I wouldn't know that suddenly my effective field theory may break now.
Like just today it can die, like whatever.
Was it important that, I think Abhijit asked that, let me ask again. Suppose this island had extended well beyond
Yes.
What would have gone wrong?
So it would have then it would have been sort of a cloning type paradox. Like essentially those degrees of freedom would have to be both in the radiation and on the CFT. Because you could have waited for that mode to come out and then receive it at the boundary, and then it would be in both the radiation and your system.
Just to make sure.
Yeah.
So I would have to do this, but then
no, you don't have to do anything for that.
Oh.
Imagine that the island was outside. We just let it be.
Yes.
Then there's going to be some mode which is outside,
which comes back.
which just comes out to the boundary. So
Yes,
you have
the
two
boundary,
copies.
the boundary state would have violated.
Yeah.
In general, entanglement wedges are always bigger than causal wedge.
Yes.
And
Yes.
provided.
Yes.
So it is causal wedges are contained inside.
Yeah.
Just
For that reason. The causal wedge of the boundary is this whole region.
Nice.
And the entanglement wedge can be.
You would violate that. Basically.
Basic point, and that would violate causality somehow.
Yeah. The way to see it is that this mode will come out of the boundary, you'll have it there, but you also have it in the radiation because you were able to manipulate. So you'll get cloning paradox.
Sorry.
No.
I was just saying that so it is important that the encoding outside the causal wedge, but within the entanglement needs to be complex, right? Otherwise, you could just die.
Yeah.
So, and the fact that AdS CFT, I could just act with something now and create something, there's no horizon. So, you know what I mean? I could create a truck in the middle
Yes.
space-time.
Yes.
That doesn't violate anything, presumably, but so then why would this violate? And
no, but there, like the causal wedge is everything and the entanglement wedge is also everything.
also. So there you said that if I could do it in a local region,
then you could violate.
Then you would
you could have a problem. Yeah. There are situations where the entanglement wedge is bigger than the causal wedge, but there's no situation where it's smaller.
The two interval thing is sort of an example, I think.
Right.
What is it?
When the entanglement wedge is bigger than the causal wedge.
Entanglement is bigger. But what I want to ask is, I mean, if you create a truck in the middle or whatever, then what is the issue of locality? This is okay, you create a truck in the middle, you do some very complicated thing on the boundary. And then what was the statement?
the question was that from the field theory point of view, it seems very non-local, but it's not shielded by horizon. You're creating a truck in a place that you can see.
Yeah.
Here you can only create things in a place that you can't really see it. Listen, it won't affect you later.
Yeah.
I was wondering whether that was important. It doesn't seem to be important for that, right?
Yeah.
That you can create trucks in places which can then come back to you is fine.
Yeah, if you have access to the whole boundary.
Business using the entire boundary, it would be nice to put it on some firmer uneasiness.
Yeah, we've discussed this, right?
Just uneasiness at this point. I mean, what is the issue? That I think it would be nice to identify that.
It would be nice. I mean, I as we discussed, I think what would be nice is a bulk local description of that.
Creating
the truck.
No, but I don't think there is a local description.
Well, something like local. For instance, if you create a charge object in there, you should violate Gauss law.
Yes.
So to understand those kind of things.
Yeah. Okay.
Semi-local, something that doesn't completely.
I absolutely agree. I will say something about that.
And I think this Wilson line idea was quite nice. We never pursued.
I mean, one thing that this one by one Hilbert space got me really confused. I always thought that it might be some non-perturbative effect. That is, I mean, if you're going to violate just from the point of view of the bulk, because the boundary can also be thought of as a part of the bulk, right?
Yeah.
I mean, just the boundary of the bulk. If you're going to do something on the boundary and immediately change something at the center, if you obviously have a breakdown of more usual notions of semi-classical gravity.
Yes, yes.
So I was thinking it has to be some exponent, e to the 1 over g Newton effect.
No, it's not complex in that sense.
It's something you could do perturbatively in g Newton. I mean, that sounds too easy to me. I don't know.
Yeah.
But like something saying HKLL is one thing, but HKLL is non-local in time.
But then
you
you can time evolve from
in
it.
the on Hilbert space.
Which that's why I keep coming back to this. But I don't know. You really think in perturbation theory in G Newton you can create a truck in the center?
Well, it depends on what you mean by perturbation theory. It's like this is some complicated operation on the boundary. It's not very local in the bulk.
Let me say something that we discussed at lunch several times but never took forward. Okay, suppose your truck is traced Z to the end.
Yeah.
You want to create trace Z to the end in the center. We can try to do this in a supersymmetric way. So I have some control.
Right.
Trace Z to the end half BPS. That's really great. Okay. Now you can ask, what can you do to create trace Z to the end? What do you have to act on? Since it's supersymmetric, presumably what you want to act on is a supersymmetric operator.
Yes.
And the supersymmetric operators in their hand are supersymmetric with the Z insertion.
Yes.
Okay. So I think you should be able, it will not be hard if you sit down to do it, to find what supersymmetric Wilson loop you have to act on with the vacuum to create trace Z to the end of the bulk.
So trace Z to the end is the operator in the field theory.
The graviton Hilbert.
The graviton.
The graviton Hilbert. I want a wave packet of those supersymmetric guys.
Got it.
Okay. Now, I don't think it would be too hard to find it. To set it up, at least in some, with assuming some renormalization and so on, to figure out what you would have to do. Now it's really cool. I think a really interesting question to ask: what will happen in the bulk? And we know more or less what will happen because we know that Wilson loops are due to strings.
Yeah.
So what I think will happen, as we discussed, is that there will be a Euclidean string world sheet that will rush in from the bound, and then the string will collapse into a bigly thing and then go up. And that will be the trace Z to the end. Okay? So you will send in a Euclidean instanton, which is a string world sheet. And then it will start rotating and become trace Z to the end of the bulk. And that will allow for charge conservation, for everything. At least there will be some effective field theory description of this. Now we can then ask our questions about causality, locality and so on. But I think it should be that the bulk totally breaks down. That something appears out of nothing. Because charge, for instance, has to be conserved. Something like this, I think.
There were some people which talked about that, right?
This was the Susskind, not exactly this. This was a precursor.
Yeah, precursor of it.
Yeah.
Okay.
Yeah, there are precursors.
Yeah. But I think this does feel.
Is it even to be a Wilson line? You want to get that?
Because you need to get something right in the middle, you need something non-local all the way. If you have something over this region, you will only be able to create something pretty near the boundary line. So if you want to get the guy right in the middle, you need the Wilson, you need something all over the place. And I think it will be a Wilson line. Okay. And then that is a Wilson line is nice because that's the boundary of an extended object.
Yes.
And an extended object naturally can do this. And then it will go up. And I think it would be sort of cool to make that, because it's a much simpler question on all this black hole business. A very simple, elementary question. I think it would be cool to make that precise. Once, if you can do a calculation, really find the instanton.
Right.
And not some calculation, some gravitational path detector, it's clean calculation. Then somehow that always leads to progress.
Well, that sounds great. I don't fully understand, but let me just say sorry, but that at least it would be suppressed, if not by 1 over g Newton, by alpha.
Yeah, it would.
But there'd be an exponential suppression.
There would be, and it would have to be something.
Yeah.
But it would be interesting that it's not per minus n square if it's true.
Yeah.
And then work with it, right? And the solution we can try to do things with it.
So why would it be alpha prime?
Because string world sheet.
Saying it's a string, but it sounds reasonable.
E to the power minus lambda.
But this is supersymmetric.
Supersymmetric, but still the string world sheet has area of string world sheet, and it will be with the disk. Even supersymmetric Wilson lines have an E to the power minus lambda.
It's sort of nice because it would give us an interpretation of some tunneling event, right? You're
It make it clear that space-time is not breaking. This instanton will be on the string, a string instanton, not a Newtonian, not Einsteinian. Because it cannot break down unless there's an end.
And maybe we can see the shape of this also by doing some experiments.
Yeah.
By doing some correlators, we can see the shape of this also.
Yeah. This is, I think, this is a real calculation. But what I mean by real calculation is a string while sheet compute the instant on.
Yeah.
It's like a fundamental theory calculation. Sort of feels nice. But well, I mean, one has to take it forward beyond lunchtime.
Yeah.
See, I was thinking you would have a bunch of operators going off at the same time, but this is more easier.
Nicer.
It's easier calculation.
Yeah. What will buy you control, if we can do it, is to focus on superset. Because that will cut down the possibilities enormously.
Yeah.
There should be some suppression. This is great, very concrete, but there should be at least some suppression. If it's just perturbation, it seems too easy.
I totally agree. I also feel do with more computations, right? More precise computations. It feels like an opportunity.
The suppression comes from, like, it will be an infinite area worldsheet.
But that infinite area is made mostly renormalized. The renormalized value of that Wilson line will not be infinite. Okay? So that will be some finite. But as Sandeep says, e to the power minus lambda to the 1. So it will be somehow, when there's a good spacetime interpretation, suppressed, but not an n square. Because we're not trying to create an object of energy n, consistent with all curves.
They should be symmetric though, right, in time.
Yeah, this is confusing.
Yeah.
Confusing,
Yeah.
causality is confusing.
Yeah.
Which path does it choose? In fact, it seems to be the only reasonable path is the light.
Yeah, I mean,
But then is it forward light going to
exactly. This is the problem with this kind of.
Yeah.
This,
Maybe
it has to happen instantaneously, right? Exactly, right.
it happens instantaneously on the boundary. Okay.
No,
But then
the one-
maybe it's the past light going then. Maybe past plus future.
I was
But it has to be
thinking it would
symmetric.
go along the time reflection symmetric slide.
No, but you won't always have a time reflection symmetric side. How does it pick a
So
slice? It's going to be like.
for now, let's just stick to this.
Yes.
It might go along the time reflection symmetric slice.
This is a Euclidean spectrum.
But then you see, you could create this and change the state everywhere within the causal wedge of this. So you also have changed the state below this. So that won't explain that, right?
But that's a question of how you're evolving this. Then there would be a time for, right? You evolve it in the future and past.
I will do to my Wilson line what it takes to create a state here.
Yeah.
Then it can't go like this, really.
But within the light.
Yeah, maybe it will matter about what you do to your Wilson. Maybe that's the point. I mean, just a little detail.
Yeah, depending on what you do, you can achieve any slice.
Any slice, yeah, maybe something.
But let's say any slice is fine, but still truck is moving in time.
That's great.
And how about here?
Yeah, okay. Actually, that is a very good question.
Yeah, it should be time symmetric, right? Like,
Usually not.
The tunneling part is computed in a universal way, and whether it's going from left to right of the barrier, that's the initial condition, right? I mean, you compute the exponential suppression through the Euclidean correlator, and then its interpretation in the Lagrangian setting depends on the initial conditions, right? I mean, that's wave packet could be coming from the left or the right.
Yeah, there should be something in your calculation that
Right.
Just like any instant on.
Yeah.
Yeah, that's.
Yeah, it should be something that is.
I thought you were describing
Yeah,
the
that kind of thing.
Yeah.
But it would be nice to see exactly where in your calculation you break the symmetry.
Yeah.
It feels like something you could do.
So the Euclidean calculation would be symmetric, yes.
Yeah.
Should be.
I mean, maybe you have to do something particular to move to the future rather than move into the past.
Yeah.
I think that's what something is.